Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're going to wander toward one of the quietest and strangest ideas in all of physics. Not a roaring explosion, not a flashing beam of light, not a black hole tearing at the fabric of space, but something much slower, much calmer, and in a way much more powerful. We're going to ask what happens when entropy reaches its limit. It sounds a little dramatic at first, as if the universe has a cluttered attic somewhere, and one day the door simply refuses to close. But entropy is not just mess in the ordinary sense, not just a pile of laundry on a chair or a desk, slowly vanishing beneath papers, cups, cables, and mysterious crumbs. Entropy is a way of describing how energy spreads out, how order becomes harder to maintain, and how the universe seems to move, gently but persistently, from concentrated possibilities toward a state where almost everything is evenly distributed, quiet, and difficult to change. So before we go any further, let me ask you something simple. Where are you listening from tonight, and what is the world around you doing right now? Is it late where you are, with the room dim, and the day slowly loosening its grip? Is there rain at the window, a heater humming nearby, a city murmuring somewhere beyond the glass? Or are you listening in the morning, letting these thoughts drift beside you while the day is just beginning? It is fitting to ask, because entropy is not only something that belongs to distant stars in the remote future of the cosmos. It is here too, in the cooling cup of tea beside you, in the battery of a phone slowly running down, in the warmth leaving a room after the heating switches off, in the way every living thing must keep taking in energy just to hold itself together for a little while longer. Entropy is not far away. It is one of the quiet background rules of being here at all. And if this sort of gentle journey through science helps you settle down, think a little more calmly, or simply enjoy the feeling of learning without having to hurry anywhere, I would be very grateful if you liked the video and perhaps subscribed. It helps this small corner of sleepy science find others who might need a peaceful place to rest their thoughts. No pressure, of course. Entropy already gives us enough pressure in the long run, although to be fair, mostly it gives us the opposite of pressure, spreading everything out until the universe is less like a tightly packed suitcase and more like one sock in every possible drawer. The topic tonight may sound enormous, because it is. We're not just talking about what happens to a room when it gets messy, or why coffee cools down, or why ice melts in a warm drink. We're talking about the far future of everything. Every star, every planet, every galaxy, every glowing cloud of gas, every black hole, every last drifting particle. We are asking what happens when the universe has used up nearly all of the useful differences that allow things to happen. A difference in temperature lets heat flow. A difference in pressure lets winds blow. A difference in energy lets machines run. Bodies live, stars shine, and chemistry unfold. When there are differences, there can be action. When everything becomes too evenly spread, when there are no strong contrasts left to draw from, the universe becomes less able to perform work, less able to build new structures, less able to surprise itself in the ways we recognize. That is the heart of entropy. It is not exactly destruction. It is not a villain. It is not the universe being careless. It is more like a tendency, a statistical drift, a preference so reliable that we call it a law. Hot things cool down when placed in cooler surroundings. Perfume sprayed in one corner of a room spreads through the air instead of gathering itself neatly back into the bottle. Smoke disperses, waves flatten. A sandcastle loses its shape under wind and water, while the beach does not usually arrange itself into a sandcastle by accident. These examples seem ordinary, even obvious, but hidden inside them is a profound direction. They tell us that nature has a habit of spreading energy and matter into more likely arrangements. There are far more ways for air molecules to be scattered around a room than for them all to huddle politely in one corner. There are far more ways for a broken cup to lie in pieces than for those pieces to leap together and become a cup again. Nothing in the deepest equations always forbids strange reversals, but the odds are so overwhelmingly against them that life unfolds in only one direction. This is why entropy is tied so closely to time. We know the past from the future not because every microscopic law has a little arrow stamped on it, but because entropy gives the world a direction we can actually experience. You can watch a candle burn down, but not burn back up. You can watch a drop of ink spread in water but not see it calmly collect itself again into a perfect drop. You can remember breakfast but not next Tuesday. In our daily lives, time is so familiar that we barely notice how strange it is. It seems to flow, to carry us along, to move from what was into what is, and then into what might be. But physics asks where that sense of direction comes from, and entropy is one of the most important answers we have. The future is the direction in which entropy tends to increase. That may sound a little gloomy, especially in a sleep video, but it does not have to be. Entropy is not simply decay. Without it, nothing familiar could happen. Heat would not flow from the sun to Earth, weather would not move, food would not release energy in the body, stars would not shine. Life itself depends on entropy, not because living things are messy in a sloppy sense, although some of us do have drawers that would make a physicist raise an eyebrow, but because living things maintain their own internal order by increasing disorder elsewhere. A plant builds sugars from sunlight and air, creating delicate structures within itself, but it does so while the sun radiates energy into space. Your body keeps its temperature, repairs cells, thinks thoughts, and moves through the world, but it must constantly take in food and release heat. Life is not a rebellion against entropy. It is a temporary local pattern made possible by a larger flow of energy from concentrated sources to more spread out destinations. This is one of the quiet surprises of the subject. Entropy does not mean nothing interesting can form. It means that interesting things form in the path of energy spreading out. A river can carve a valley because water falls from higher ground to lower ground. A storm can organize itself because warm and cool air are exchanging energy. A star can hold itself together and shine because gravity has gathered matter into a dense place, and nuclear processes inside it send energy outward. Even a living cell is a tiny island of order maintained by constant exchange with its environment. The order is real, but it is not free. It is paid for by the wider increase of entropy around it. In that sense, every flower, every heartbeat, every thought, and every sleepy scientific question is part of the universe spending its energy differences. So when we ask what happens when entropy reaches its limit, we're asking what happens when the universe has spent nearly all of those useful differences. What happens when there are no bright stars left to warm planets, no fresh fuel left to make new suns, no great temperature gaps left to drive complex processes, no concentrated energy left in forms that can easily be used. It is a question about the end of change as we understand it. Not the end of existence exactly, because something may still remain, but the end of the kind of active, structured, flowing universe we live in now. The phrase often used for this future is heat death, although it is a slightly misleading phrase. It does not mean everything becomes hot. In fact, it means almost the opposite. It describes a state where energy is so evenly spread out that there is no useful flow left. No hot here and cold there, no strong gradients, no cosmic engine, no easy way for anything to happen. Imagine a bath of warm water. At the beginning, one end might be hot and the other cool, and you could feel the difference with your hand. Heat would move from the warmer region into the cooler one until the whole bath became the same temperature. Once that happens, the water has not disappeared, the energy has not vanished. But the difference that allowed heat to flow has faded. There is still motion in the molecules, still microscopic activity, but from the point of view of large-scale usefulness, the bath has reached a kind of balance. It no longer has a hot side and a cold side that can do anything interesting together. Now imagine that idea stretched across the entire universe, not for minutes in a bathtub, but for unimaginable spans of cosmic time. That is the kind of limit we're approaching in this story. Of course, we should be careful. Physics does not always hand us final answers wrapped neatly with a ribbon. The ultimate fate of the universe depends on many things, including dark energy, the expansion of space, the behavior of black holes, and the deep laws connecting gravity, quantum mechanics, and thermodynamics. Some of these are well understood, others remain mysterious. But the broad picture from modern cosmology is that the universe appears to be expanding, and that expansion is not slowing down in the simple way scientists once expected. Space itself is stretching, carrying distant galaxies farther apart. Over immense time, stars will age and die. New star formation will slow as gas is used up or locked away. Galaxies will dim. The bright era of the universe will fade into a colder, darker, thinner future. Black holes may become the last major objects, slowly losing energy through processes that are almost unimaginably slow. After that, if our current understanding holds, the universe drifts toward a state where little remains but faint radiation, isolated particles, and a vast emptiness with almost no usable structure. It is difficult for the human mind to hold such timescales. We are used to days, seasons, lifetimes, perhaps history measured in centuries or civilizations measured in thousands of years. The future of entropy asks us to think beyond stars, beyond galaxies as bright homes, beyond any clock we could build or any story we could comfortably tell. And yet, it begins with things we know intimately. The warmth leaving your hands on a cold mug, the way a room cools after sunset, the way a wound must be repaired by energy from food, the way a battery once drained cannot power a device unless energy is put back into it. The cosmic ending is not separate from these everyday patterns, it is the same tendency, repeated on the grandest possible scale. There is something strangely calming about that, if we approach it gently. The universe is not rushing toward this limit in any human sense. It is not late. It is not panicking. It is not checking its watch and muttering that it should have left earlier. Entropy works through probability and time, and the universe has time in quantities that make our daily urgency look very small. The stars still shine, planets still turn, clouds still form, minds still wonder. We are living in a rich middle period, a time when energy differences are abundant enough to make complexity possible. The sun pours light into space, Earth catches a tiny fraction of it. Life uses that flow to build forests, oceans full of motion, animal bodies, nervous systems, memory, language, and eventually someone lying comfortably somewhere, listening to a quiet voice talk about the heat death of the universe, as if it were a bedtime story. Physics can be odd like that, and perhaps that is one reason this question matters. Asking about the limit of entropy does not only tell us about the far future, it helps us understand why the present is so full of activity. We notice the world because it is not in perfect balance. We exist because the universe is not already at maximum entropy. There are still differences to be used, flows to ride, structures to form, and patterns to maintain for a while. Every living thing is temporary, but temporary does not mean meaningless. A flame is temporary, yet while it burns, it gives light. A song is temporary, yet while it plays, it has shape. A thought is temporary, yet it can change what happens next. Entropy reminds us that everything physical has a cost and a direction, but it also reminds us that the universe is currently rich with the conditions that allow order to appear in pockets, to persist for a while, and to become aware of itself. So tonight we will move slowly into that idea. We will begin not at the end, but with the basic behavior that points toward it. We will look at why energy spreads out, why order requires effort, why time seems to have a direction, and how stars, life, black holes, and the expansion of space all fit into the same broad thermodynamic story. We will not hurry to the final silence. There is too much to notice along the way. Entropy is often introduced as disorder, but that simple word can mislead us if we lean on it too heavily. A messy bedroom is not the same thing as a universe approaching thermodynamic equilibrium, and a neatly made bed is not a loophole in the laws of nature, although it may feel like one on a tired morning. To understand the real idea, we need to think less about mess as an opinion and more about possibilities. How many ways can a system be arranged while still looking the same from the outside? How many microscopic details are hidden beneath the simple appearance of a warm cup, a cold room, a glowing star, or a quiet patch of space? That is where the story begins to deepen. Entropy is not a mood. It is not nature being untidy. It is a measure of how energy and matter can be arranged, and why some arrangements are common while others are rare. A deck of cards in perfect order feels special because there are so many more ways for it to be shuffled. A cloud of gas filling a room feels ordinary because there are so many ways for its molecules to spread out. A star is special because gravity has pulled enormous amounts of matter into a dense hot body, creating conditions that can shine for billions of years. But even that shining is part of a larger spreading, a long release of energy into the wider universe. The star holds itself together for ages, and all the while it is giving itself away. So settle in now. Let the room be as it is. Let the clock, if there is one nearby, do its quiet little job without needing your attention. We're going to start with the simplest version of the question, the one hidden inside cooling tea and fading warmth, and rooms that never tidy themselves without help. Before we can understand what it would mean for entropy to reach its limit, we need to understand why the universe seems so determined to spread things out in the first place. Entropy begins in ordinary places. It begins in a kitchen after dinner, when the warmth from the oven drifts into the room and then slowly fades. It begins in a mug of tea that was too hot to drink a few minutes ago, and now is becoming just right, and later will become disappointingly lukewarm if forgotten. It begins with a stack of papers that somehow becomes less stack and more landscape, with blankets that never seem to fold themselves, and with dust that arrives quietly from no obvious source, as if the universe has a subscription service for tiny inconvenience. These are small things, familiar things, but they point toward one of the deepest patterns in nature. Left alone, energy tends to spread out. Ordered arrangements tend to become less special. Useful differences tend to soften. The world does not usually become simpler in the way we want it to. It becomes more probable. That word, probable, is the key. Entropy is often described as disorder, and that is a useful first step, but it can also be a little misleading. Disorder sounds like a judgment. A child might call a room messy, while a cat might see the same room as a perfectly arranged obstacle course. Physics is not really concerned with whether the laundry is on a chair or in a drawer. It is concerned with how many microscopic ways something can be arranged while still looking the same to us on the outside. A tidy arrangement is usually special because there are fewer ways to make it. A messy arrangement is usually common because there are many more ways to make it. The universe, given enough time and without careful guidance, tends to wander from rare arrangements into common ones, not because it has a plan, but because common arrangements are simply easier to find. Imagine a deck of cards placed in perfect order, the suits arranged neatly, the values rising one after another, everything exactly where it should be. That arrangement is possible, but it is very particular. If you shuffle the deck, it is overwhelmingly likely that the cards will end up in an arrangement that looks random. Not because the cards prefer chaos, not because shuffling is malicious, but because there are vastly more mixed arrangements than neatly ordered ones. If you shuffle again, you do not expect the original order to return. It could, in principle, but the chance is so tiny that you would not build your afternoon around it. This is close to the way entropy works. It is not that nature forbids order, it is that disorder, in the physical sense, has so many more available forms. A cup of hot tea cooling on a table gives us a gentler version of the same idea. At first, the tea contains more concentrated thermal energy than the air around it. There's a difference between the hot liquid and the cooler room. Because of that difference, energy flows outward. Warmth moves from the tea into the cup, from the cup into the air, from the air into nearby surfaces, and eventually into the wider surroundings. The tea cools. The room warms by a tiny amount, so tiny you would not notice unless you had very sensitive instruments and perhaps a suspiciously intense relationship with beverages. The important thing is that the energy has not vanished. It has spread. It has become less concentrated, less available for doing noticeable work. The tea has not lost its energy into nothingness. Its energy has become harder to use. That is one of the most important lessons entropy teaches. Energy is conserved, but usefulness is not. The total amount of energy in a closed system remains the same, but the energy can become spread out in ways that make it less able to drive change. A charged battery can power a phone because it contains energy arranged in a useful difference. Once the battery drains, the energy has not been destroyed. It has been transformed and spread into heat, light, motion, radio signals, and countless tiny changes in the surroundings. But you cannot simply gather that scattered energy back into the battery without effort. You have to plug it in. You have to bring in organized energy from somewhere else. This is why entropy matters so much. It is the difference between energy merely existing and energy being available. A room can be cleaned, of course. A bed can be made. A broken machine can be repaired. Living things can grow into highly ordered forms. Snowflakes can form delicate patterns. Crystals can assemble into precise structures. Entropy does not mean that order is impossible. That would be a very dull universe, and also a difficult one in which to explain trees, brains, or the suspiciously neat rows of snacks in a supermarket. Order can appear locally when energy flows through a system. But that local order comes with a cost. A person tidies a room by using energy from food, and the body releases heat. A plant builds itself using sunlight, while energy from the sun spreads into space. A refrigerator keeps its inside cool by pushing heat outward into the room, which is why the back of the refrigerator is warm. Order in one place is maintained by increasing entropy somewhere else. This is why life does not violate entropy. Life is not a magical exception to thermodynamics. It is one of thermodynamics' most elaborate performances. A living cell is full of organized structures, membranes, proteins, genetic information, chemical gradients, tiny machines doing very specific jobs. It looks like a rebellion against disorder, but the cell is not closed off from the world. It takes in energy and matter. It releases waste and heat. It maintains its internal order by contributing to a larger spreading of energy around it. Your body does the same. Every thought, every breath, every slow blink while listening to this depends on energy being processed and dispersed. You remain organized because you're not isolated. You're part of a flow. That flow is everywhere. The sun shines because matter in its core is transformed under extreme pressure and temperature, releasing energy that travels outward. By the time sunlight reaches Earth, it has crossed a great distance and become part of weather, ocean currents, plant growth, warmth on skin, and eventually heat radiating away again into space. Earth is not a closed box sitting quietly in the dark. It is bathed in energy from a hot star and releases energy into a much colder universe. This difference allows astonishing things to happen. Winds blow, water evaporates, clouds form, rain falls, rivers move, forests grow, animals walk, and human beings develop the ability to worry about the long-term fate of the cosmos while misplacing their glasses. The same pattern appears at larger scales. Stars form from clouds of gas because gravity pulls matter together. At first, that may sound like entropy decreasing, because a spread-out gas becomes concentrated into a star. But gravity has its own strange relationship with entropy. When matter gathers under gravity, it can heat up, radiate energy away, and create conditions where the total entropy still increases. The star becomes an ordered object in one sense, a glowing sphere with structure, layers, pressure, and balance. but it also becomes a powerful source of radiation, pouring energy outward into space. Gravity creates pockets of order that then become engines of entropy increase. It gathers matter so that energy can be released in new ways. The universe is subtle like that. It does not simply smear everything out at once. It builds temporary structures that help the spreading continue. This is why entropy can feel paradoxical. If the universe tends toward disorder, why are there galaxies, stars, planets, molecules, oceans, and living things? The answer is that entropy does not require the universe to be featureless at every moment. It describes the overall direction of change. On the way toward greater spreading, structure can form. In fact, structure often forms because it is an effective pathway for energy to disperse. A hurricane is highly organized compared with calm air, but it forms because heat from warm ocean water is moving into the atmosphere. The swirling order of the storm is part of a larger process of energy redistribution. A flame has shape and motion, but it exists because chemical energy is being released and spread as heat and light. A living forest is richly ordered, but it grows in the path of sunlight flowing from a hot sun into cold space. Order is not always the opposite of entropy. Sometimes order is the channel entropy uses. At the human scale, entropy explains why maintenance is not optional. Houses decay if neglected. Metal rusts. Food spoils. Muscles weaken without use. Memories fade if not revisited. A garden becomes overgrown. Paint flakes. Machines wear down. None of this is because nature has a personal grudge against weekend plans. It is because organized systems are specific arrangements, and specific arrangements require conditions that keep them from drifting into more common ones. A wooden fence stands because its structure resists the environment, but rain, sunlight, temperature changes, fungi and insects all offer pathways for that structure to change. To keep it as a fence, someone must repair it, treat it, replace parts, and spend energy. Order persists when energy and attention are supplied. Without them, the system explores other possibilities. This is also why time seems to have a direction. We do not see ice cubes forming spontaneously in warm water, because that would require scattered thermal energy to concentrate itself in a very particular way. We see ice melt because there are many more ways for its ordered crystal structure to break down as heat spreads into it. We do not see smoke return neatly into a candlewick after drifting through a room. We see it disperse because the dispersed arrangement is far more likely. We do not see a shattered bowl assemble itself from the floor because the pieces would need an astonishingly precise set of motions all at once. We see bowls break because there are many ways for impact energy to scatter fragments. Entropy gives everyday reality its before and after. There is a quiet seriousness in this. The past is usually more ordered in the ways that matter to us. The future is usually more spread out. A photograph can fade, but faded colours do not casually regain their original brightness. A warm loaf of bread cools, but a cold loaf does not draw heat from the room and become fresh from the oven again, although that would be a very popular feature in kitchens. The direction feels natural because we have never lived outside it. Our brains themselves depend on entropy increasing. To form a memory, physical changes occur in the brain. Energy is used, heat is released. The act of remembering is part of the same thermodynamic world as burning fuel or cooling tea. We remember the past because the past has left traces in the present. The future has not yet left traces because those physical processes have not happened. Entropy also helps explain why perfection is fragile. A perfectly smooth surface, a precisely stacked tower, a carefully arranged pattern, a cleanly folded shirt. These are all special conditions. They can exist, but they are vulnerable because there are many more ways for them to become less perfect than more perfect. One bump can topple a tower, one spill can stain a shirt. One careless elbow can turn a neat desk into an archaeological site. In the microscopic world, constant motion is always present. Atoms and molecules jiggle, collide, rotate, vibrate, and exchange energy. Even solid objects, which feel still in your hands, are full of internal motion. The calm surface of matter hides a restless interior. Entropy is connected to that hidden restlessness and to the number of ways it can be arranged. The early universe presents one of the deepest puzzles related to entropy. If entropy tends to increase, then the universe must once have been in a lower entropy state than it is now. Observations suggest that the early universe was extremely hot and dense, but also surprisingly smooth and uniform. That smooth beginning gave gravity room to work. Tiny differences could grow. Matter gathered into the first stars and galaxies. Those structures then produced heavier elements, planets, chemistry, and eventually life. If the universe had begun already at maximum entropy, there would have been no useful differences, no cosmic development, no stars switching on, no history in the way we understand it. The fact that we are here means the universe began in a state with room for entropy to increase. Why it began that way remains one of the great open questions in physics. This matters because the story of entropy is really the story of available possibility. A low entropy state is not merely neat, it is a state with potential. A wound spring can move a clock, a raised weight can fall and turn machinery, a hot star can warm a cold planet. A concentration of chemical energy can power a cell. A difference can do something. As entropy increases, those differences are gradually reduced. Energy becomes more evenly distributed. The spring unwinds, the weight falls, the hot object cools, the fuel is spent. Change still exists at microscopic scales, but the large-scale ability to drive organized processes decreases. This is why the limit of entropy is so important. It is the point where the universe would still contain energy, but almost no usable differences. For now, though, we're nowhere near that limit in any immediate sense. The universe is still filled with contrast. Stars burn against dark space. Galaxies gather in vast structures, planets orbit. Black holes pull matter into extreme regions. Young stars form in clouds of gas, though not forever. Life on Earth continues to use the sun as a source of low entropy energy, turning light into complexity, motion, warmth, and thought. We live in a universe that is aging, yes, but still active. Entropy is increasing, but the increase is not a simple slide into dullness at every scale. It is a long, uneven unfolding, full of temporary islands of structure. The universe is not like a room becoming messy in one afternoon. It is more like an immense system of flows, where order appears, transforms, and disappears as energy spreads through every available route. Thinking about entropy this way can make the subject feel less bleak and more grounded. It is not just the reason things fall apart, it is also part of why anything happens at all. A world with no entropy increase would be a world without cooking, breathing, weather, metabolism, memory, aging, fire, friction, digestion, or stars. It would be a world with no meaningful direction from one moment to the next. Entropy is woven into the fact that events occur. It is why a cause leaves an effect, why warmth moves, why systems change, why the present carries marks of the past. It is one of the reasons the universe is not frozen in a single unchanging arrangement. Even the word mess deserves some kindness. In daily life, mess means inconvenience. In physics, what we call disorder is often just abundance of possible arrangements. A gas filling a room is not failing to behave, it is doing what is most likely. Heat spreading into cooler surroundings is not wasteful from nature's point of view, it is ordinary. It is the expected path. When we create order, we're not defeating the universe. We're working within its rules, using flows of energy to make temporary patterns. A book, a house, a body, a civilization, a song, a scientific explanation spoken softly at night. All of these are patterns held together for a time. They do not last forever, but while they exist, they are real. This is where entropy becomes more than a technical idea. It becomes a way of seeing the present clearly. The warmth in a room is temporary. The stars are temporary. Our bodies are temporary. Even galaxies are temporary on long enough timescales. But temporary does not mean accidental or unimportant. A candle flame is temporary because it is a process, not a fixed object. Its beauty is inseparable from the fact that fuel is being transformed and energy is being released. Life is similar. A living thing is not a statue that resists time. It is a continuous activity, a maintained pattern, a flow of matter and energy with a name. You're not the same collection of atoms you were years ago, yet the pattern continues. Entropy does not erase the wonder of that. It helps explain how delicate and active that wonder is. As the universe moves onward, entropy will keep increasing in the overall sense. The available differences will slowly decline. Stars will use their fuel, hot objects will radiate, matter will change forms, structures will merge, collapse, evaporate, or drift apart. The great cosmic story is not a simple fall from order to mess, but a gradual spending of possibilities. Right now, there is still plenty to spend. There is sunlight in the morning, warmth under blankets, the small chemical energy of a late-night snack, and the electrical order inside the device carrying this voice to you. All of it depends on differences that have not yet been exhausted. So when we picture entropy as the universe's gentle slide toward mess, we should imagine something quieter and more precise than a room getting untidy. We should imagine energy losing its sharp contrasts. We should imagine rare arrangements giving way to more common ones. We should imagine structures forming where energy flows, then fading when those flows run out. We should imagine not a disaster but a direction. Not a sudden collapse, but a persistent tendency written into ordinary experience. The same rule that cools the tea, drains the battery, melts the ice, ages the stars, and gives time its familiar one-way feeling. And from there, the next question rises naturally. If entropy is about energy spreading and useful differences fading, why does energy spread out at all? Why does heat leave the tea instead of gathering more tightly inside it? Why does smoke fill the room instead of waiting politely in one corner? Why does nature choose the common arrangement so reliably that it becomes one of the foundations of physics? To answer that, we need to look more closely at the hidden crowd beneath every ordinary object, the countless particles moving, colliding, sharing and rearranging themselves while the world above them seems calm. Energy spreads out because there are more ways for it to be spread out than for it to be concentrated. That is the simple sentence at the centre of the idea, though it takes a little time to feel how much it explains. Nature is not choosing mess with a mischievous grin. It is not looking at a hot cup of tea and deciding that someone should be mildly disappointed in 20 minutes. It is following probability. When energy has many available places to go, and no wall or machine or living process is forcing it to stay gathered, it usually moves into those available places. Not because each tiny piece of matter knows the plan, but because, when countless tiny motions are added together, the spread-out arrangement wins almost every time. Think again of the tea, because tea is patient with physics and rarely complains about being used as an example. At the beginning, the tea is hotter than the air around it. That means the molecules in the tea are, on average, moving more energetically than the molecules in the surrounding air, the ceramic cup and the table beneath it. Inside the liquid, molecules are jostling, colliding, twisting and transferring energy to one another. At the surface, they collide with molecules in the air. Along the walls of the cup, they transfer energy into the ceramic. The cup then passes energy into the surrounding air and into your hand if you are holding it. No single molecule announces that the tea must cool down. Each collision is local. Each exchange is small. But with enormous numbers of molecules involved, the overall result becomes reliable. Energy flows from the hotter region into the cooler surroundings until the difference softens. That phrase, on average, matters. At microscopic scales, the world is restless and uneven. A few molecules in a cool room may be moving quickly. A few molecules in hot tea may be moving more slowly. There is always variation. But temperature is not about one molecule. It is about the average behaviour of a huge crowd. When a hot object touches a cool one, fast-moving particles tend to transfer some of their energy to slower-moving particles through collisions and interactions. There can be small exceptions here and there, tiny local transfers in the opposite direction, but the overall movement is from concentrated thermal energy toward a more shared distribution. A crowd leaving a theatre gives a helpful picture. One person might turn back to look for a scarf, another might pause to check a phone. But if the doors are open and the show is over, the crowd as a whole moves outward. This is why energy spreading is not a mysterious force pulling everything toward dullness. It is a statistical outcome. There are simply more possible arrangements in which energy is shared among many particles than arrangements in which it remains packed into one small place. If you drop a little food colouring into a glass of water, it begins concentrated. At first there is a coloured patch, a tiny region where the dye molecules are gathered. Then the dye spreads. Water molecules bump into dye molecules. Dye molecules wander, collide, and drift. After a while, the colour becomes evenly mixed throughout the glass. Nothing has forced each dye molecule into a perfect plan. They are moving randomly, but random motion in a system with room to explore leads to mixing. The evenly spread state is not more organised in the everyday sense. It is more likely because there are many more ways for the dye molecules to be distributed throughout the glass than to remain packed together in a neat little drop. The reverse is not forbidden in the most basic sense. If every dye molecule happened to move in just the right way at just the right time, they could gather back together. If every air molecule in your room happened to drift into one corner, the rest of the room would briefly become a very unpleasant place to breathe. But such events are so unlikely that for ordinary purposes they do not happen. The number of possible mixed arrangements is not just larger than the number of unmixed arrangements. It is larger beyond common intuition. When the number of particles is enormous, probability becomes a law for all practical experience. That is why we do not sit in rooms worrying that all the air might suddenly gather near the ceiling. Physics permits microscopic randomness, but large numbers make the familiar world dependable. A helpful way to imagine this is to think of coins. If you toss one coin, it can land either way. If you toss a few coins, you might sometimes get all of them landing the same way. But if you toss a vast number of coins, the chance that every single one lands the same way becomes so tiny that it may as well be impossible in ordinary life. Most results look mixed. Not because mixed results are commanded by a ruler, but because there are so many ways to be mixed. Energy behaves similarly when shared among countless particles. A perfectly concentrated arrangement is like all the coins landing the same way. A spread out arrangement is like a messy mixture of outcomes. The mixed condition appears again and again because it has far more paths leading to it. This is the reason hot things cool and cold things warm when they are placed together. If you put a warm stone into cool water, the fast-moving particles in the warm stone interact with the slower-moving particles in the cooler water. Over time, energy becomes more evenly shared. The stone cools, the water warms, and eventually they reach the same temperature. Once they are at the same temperature, energy is still moving microscopically in both directions, but there is no net flow that you can use. The busy exchange continues, yet the large-scale difference has vanished. This is one of the quiet facts that makes entropy so important. Motion remains, but usefulness declines. Energy is still there, but it no longer has the same ability to drive change. The spreading of energy happens in different ways depending on the material and the situation. In solids, heat moves as neighbouring atoms and molecules pass motion along through their bonds. The object may seem still, but internally it is vibrating. Warm one end of a metal spoon and those vibrations pass energy along the spoon toward the cooler end. In liquids and gases, heat can move through direct contact, but also through the motion of the fluid itself. Warm air rises because it becomes less dense than cooler air around it, and cooler air moves in to take its place. This creates currents that carry energy through a room, an ocean, or an atmosphere. Energy also spreads through radiation, which does not need air or water at all. The sun warms Earth by sending light across space. Your body radiates heat into a cooler room. A fire warms your face from across the hearth. In each case, energy moves from a region where it is more concentrated or associated with a higher temperature towards surroundings where it can be more widely shared. The universe is full of these movements because the universe is full of differences. A star is much hotter than the space around it. A planet has warm days and cool nights. The deep ocean differs from the surface. The inside of Earth differs from the crust. The body differs from the surrounding air. Every difference is an opportunity for energy to flow. Some flows are fast, like a spark crossing a gap or steam rushing from a kettle. Some are slow, like heat leaking through a wall during a winter night. Some are steady enough to become part of life, like sunlight arriving each day and Earth releasing heat back into space. The scale changes, but the logic remains the same. Energy tends to move from concentrated patterns into wider distributions. What makes this especially interesting is that spreading energy can create structure along the way. This may seem backwards at first. If energy always spreads out, why does it sometimes produce something organized? Why do we get whirlpools, lightning, storms, crystals, cells, and living bodies instead of just a bland smoothing of everything? The answer is that structure can be part of the spreading process. When a system is far from balance, organized patterns may form because they help move energy more efficiently. Warm water in a pot may develop rolling currents as heat moves from the bottom into the cooler water above. The current has shape and direction, but it exists because energy is spreading. A thunderstorm has structure, with rising air, falling rain, electrical separation, and powerful winds, but it forms because heat and moisture are being redistributed through the atmosphere. A living body is highly organized, but it persists by processing energy and releasing heat. Order can appear as a route through which entropy increases. This is one of the most important points to hold gently in mind. Energy spreading is not the same as immediate sameness. The path toward balance can be full of motion, complexity, and temporary order. When water drains from a sink, it may form a vortex. The vortex is organized, but it is also part of the process of water moving downward and energy being dispersed. When a candle burns, the flame has a recognizable shape, color, and behavior, but it is the visible sign of chemical energy being released as heat and light. When your body digests food, it builds and repairs tissues, moves muscles, and supports thought, but the full process increases entropy overall. The universe often builds little machines, natural or living, that help energy spread from where it is concentrated to where it is less concentrated. The Sun and Earth provide a larger and more important example. The Sun is a hot source of energy. Space is cold by comparison. Earth sits between them, receiving sunlight and radiating heat away. Because incoming sunlight is relatively concentrated and outgoing heat is more spread out, Earth can support complex processes. Weather is driven by uneven heating. Plants use sunlight to build chemical structures. Animals use those structures for energy. Human civilization uses stored energy from sunlight in ancient plants, as well as direct sunlight, wind, water flow, and heat from Earth. Every meal, every breeze, every green leaf, every cloud has a place in this chain. The sun is not just lighting the world. It is providing a difference that allows the world do things. Differences are the engines of action. A battery works because there is a chemical difference between its parts. A wind turbine works because air is moving from one pressure condition to another. A hydroelectric dam works because water is higher on one side and lower on the other. A heat engine works because one region is hotter than another. Your muscles work because cells maintain chemical differences across membranes and use energy from food to control molecular processes. Remove the difference and the action stops. A battery with no remaining separation cannot power a device. A lake with no height difference cannot drive water through a turbine. air at the same pressure everywhere produces no wind. A universe with no usable differences would be a universe with energy, but no large-scale ability to do work. This is why spreading energy is tied so closely to the future limit of entropy. As energy spreads, differences tend to fade. As differences fade, the capacity for change decreases. But the process is not simple or quick. Gravity complicates the picture by pulling matter together, forming stars and galaxies, and creating new sources of concentrated energy. A cloud of gas can collapse under its own gravity, heat up and ignite as a star. This looks like concentration, and it is, locally. But the collapsing matter releases energy, and the star then radiates for millions or billions of years. Gravity can create pockets where energy becomes concentrated in ways that later allow much greater spreading. It is like nature gathering wood into a pile, not to preserve it forever, but to make a fire possible. The pile is ordered, but the burning releases energy more widely. Black holes make the story stranger still. They are among the most extreme gravitational objects in the universe, formed when matter collapses into a region so dense that not even light can escape from within the boundary around it. For a long time, they seem like cosmic traps where entropy might be hidden away. Modern physics suggests something deeper. Black holes have enormous entropy, connected not to their volume in the usual way but to the size of their boundary. They also are expected to emit faint radiation over unimaginable timescales, slowly losing mass. This means even the darkest, most compact objects may take part in the long spreading of energy. The details reach into difficult territory, where gravity and quantum theory meet, but the broad message fits the same story. Concentration does not last forever without consequence. At the smallest scales, the spreading of energy is also linked to information. To know exactly where every particle is and how it is moving would require an impossible amount of detail for a large system. We describe large objects with simpler properties, such as temperature, pressure, and volume, because we cannot track every microscopic motion. Entropy is connected to the number of hidden microscopic arrangements compatible with what we observe. When energy spreads out, there are more hidden arrangements that fit the same large-scale description. A room of air at uniform temperature can be arranged in countless microscopic ways and still look like the same room of air to us. That is why the uniform state is so likely. It has a vast number of internal possibilities. This also helps explain why energy does not gather itself again in useful ways without guidance. To reverse the spreading, the microscopic motions would need to be coordinated with extraordinary precision. You can make a refrigerator cool its interior, but only by using energy from outside and releasing more heat into the room. You can charge a battery, but only by drawing organized energy from a power source. You can clean a room, but only by using effort, food energy, and time. Local reversal is possible when it is paid for by a larger increase elsewhere. Nature does not ban the creation of order. It simply requires the accounting to balance in the larger system. A house at night gives a plain example. If it is cold outside and warm inside, heat leaks outward through windows, walls, doors, and the roof. You can keep the house warm with a heater, but the heater requires energy. The warmth inside is a maintained condition, not a permanent gift. If the heating stops, the house gradually approaches the temperature of its surroundings. This is not failure. It is thermal balance arriving by many small pathways. The warm air touches cooler surfaces. The surfaces pass energy outward. Tiny drafts exchange air. Radiation leaves through windows. The house is always negotiating with the larger environment, and without a supply of energy, the difference fades. Living things do the same, but with greater complexity. A warm-blooded animal maintains its internal temperature even when the surroundings are cooler or warmer. This takes energy. Food is broken down. Cells release usable energy. Waste products and heat leave the body. The animal remains ordered, active, and alive because it is constantly participating in energy flow. When that flow stops, the body can no longer maintain its internal differences. Temperature equalizes, chemical gradients fade, structures break down. This is not just biology, it is thermodynamics expressed through biology. Life is a pattern that persists by keeping energy moving. On Earth, human technology is also a story of managing energy gradients. We burn fuels, spin turbines, store electricity, cool buildings, heat water, transmit signals, and compute information. Every device we use depends on directing energy before it spreads into less useful forms. A laptop becomes warm because not all electrical energy remains available for computation. A car engine releases heat because fuel energy cannot be converted entirely into motion. A light bulb warms its surroundings while producing light. Even efficient machines produce some waste heat. Not because engineers are careless, though occasionally a tangled cable drawer might suggest otherwise, but because energy transformations naturally disperse some energy into microscopic motion that is hard to recover. The deeper you look, the more the same principle appears. Energy spreads out because spread out states are more numerous. Heat flows because collisions share motion. Matter mixes because random movement explores available space. Structures form because they can help move energy from concentrated sources toward broader surroundings. Useful differences power change, and when those differences are exhausted, change becomes harder to sustain. This is not a gloomy rule. It is the rule that makes fires burn, winds move, stars shine, and bodies live. It is the reason the universe has a story rather than a static display. And yet, there is a direction hidden inside it. Once energy spreads in ordinary circumstances, it does not naturally gather back into the same concentrated form. Once warmth leaves the tea does not reheat itself by politely asking the room for its energy back. Once perfume fills the room, it does not return to the bottle. Once sunlight has been absorbed, transformed, re-radiated, and scattered into space, it does not easily reassemble into a beam and fly back into the sun. This one-way behavior is so familiar that we build our entire sense of reality around it. We call it time passing. We call it before and after. We call it memory, aging, history, cause and effect. So the spreading of energy is more than a background process. It is one of the reasons the universe appears to move forward. It links the tiny motions of particles to the cooling of stars, the metabolism of living cells, the rise and fall of civilizations, and the far future in which usable differences may become scarce. A hot thing cooling, a gas expanding, a battery draining, a body breathing, all point in the same direction. They tell us that the universe has a preferred way of unfolding at large scales, even if the microscopic pieces are only following local rules. From here, the next step is to look at that direction itself. If energy spreading explains why some changes are likely and others are not, then it also helps explain why yesterday feels different from tomorrow, why we remember one and not the other, why broken things do not unbreak in daily life, and why the universe seems to have a one-way road built into it. That road is often called the arrow of time, and it begins with the same quiet truth we have been following all along. Energy spreads, differences fade, and the future is the direction in which entropy grows. That one-way road is so familiar that we almost never question it. We wake up before we remember waking up. We pour water before the kettle boils. We eat breakfast before the plate is empty. We send a message before someone replies, unless they are unusually fast, in which case we briefly suspect they may have been waiting with suspicious enthusiasm. Life arrives in order. Events come with a before and an after. Causes seem to stand behind effects, pushing them forward. A dropped glass falls, strikes the floor, and breaks into pieces. We do not see scattered pieces quietly rise, join at the edges, smooth themselves into a glass, and hop back into a waiting hand. We can imagine such a reversal, and films can show it easily by playing the scene backward. But the real world does not behave that way in front of us. It has a direction, and that direction is what physicists call the arrow of time. The phrase sounds simple, but it points to a deep puzzle. At the scale of ordinary life, time feels obvious. Yesterday is gone. Tomorrow has not happened yet. The present is where we stand, or at least where we think we stand, before it slips away and becomes memory. But when physicists look at the most basic laws describing particles and forces, many of those laws do not seem to care very much whether time runs forward or backward. If you could watch two ideal particles collide in empty space, and then watch the same collision in reverse, the reversed version might still obey the same basic rules. A planet orbiting a star can be described forward in time, but in a simplified perfect model, the mathematics can also describe it backward. The equations do not always contain the everyday difference between a glass breaking and a glass unbreaking. Yet our lives are full of that difference, so the question becomes sharper. If the microscopic rules often allow processes to be reversed, why does the world we experience move so strongly in only one direction? Entropy gives the most useful answer we have. The future is the direction in which entropy tends to increase. That statement does not require time to have a little arrow painted on each particle. It comes from the fact that systems with many parts usually move from rare arrangements into more common ones. A whole glass sitting on a table is a particular arrangement of atoms. A broken glass scattered across the floor is not one single arrangement, but a huge family of possible arrangements. The pieces could be spread slightly this way or that way. A shard could lie near the chair leg or closer to the wall. Tiny cracks could branch in countless patterns. The energy of impact could be shared among vibrations, sound, heat, and motion in many possible ways. There are vastly more broken-looking states than whole glass states, so when the glass hits the floor, it moves into the more probable condition. It is not impossible in the deepest logical sense for every piece and every bit of energy to reverse course exactly, but the required coordination is so extreme that it never appears in ordinary experience. This is the practical meaning of irreversibility. A process is irreversible when it can happen naturally in one direction but not naturally in the other. Heat flows from hot tea into cooler air. It does not naturally flow from the cooler air into the tea in a way that makes the tea hotter while the room becomes colder. Ink spreads through water. It does not naturally gather itself back into a neat drop. Smoke disperses. It does not naturally reassemble into the shape of the flame that produced it. Food can be cooked, but the cooked meal does not uncook itself into raw ingredients on the counter. A sandcastle can be washed flat by the tide, but the next wave does not normally rebuild the towers, carve the windows, and add a tasteful little moat. In every case, the forward process moves from a more special, more constrained arrangement to one with many more possible forms. This is why the arrow of time is not just a feature of clocks. A clock measures time, but it does not create the direction of time. A clock itself works because physical processes inside it proceed in a reliable order. A pendulum loses a little energy to friction and air resistance. A quartz clock depends on electrical energy being organized and used. An atomic clock counts steady transitions in atoms, but the device around those atoms still exists in the thermodynamic world, powered, cooled, maintained, and compared with other clocks. The ticking of a clock is useful because the universe already has processes that do not run both ways in ordinary conditions. If time had no practical direction, a clock would not be a guide through a sequence. It would be more like a decorative object with ambition. The arrow of time also explains why records exist. A footprint in wet sand tells you someone walked there. A crater tells you something struck a surface. A tree ring tells you something about a year in the tree's growth. A photograph records light that arrived at a camera in the past. A memory is a physical record laid down in a brain. These records all form through irreversible processes. The footprint appears because pressure rearranges sand and water. The crater appears because impact energy changes rock and soil. The photograph appears because light changes a sensitive surface or electronic sensor. A memory forms through changes in connections and activity inside the nervous system. The past is knowable because it has left traces. The future has not left traces in the same way. It may be expected, predicted, hoped for, or worried about, but it has not yet impressed itself physically into the present. This is one reason time feels so deeply connected to memory. We do not simply move through time like a bead sliding along a string. We carry records of earlier states inside us. Your brain is not a passive observer floating above thermodynamics. It is a warm, active, energy-using organ that constantly changes as it receives information, stores patterns, and updates expectations. To remember something, the brain must have been altered by it. Those alterations require energy and produce heat. They belong to the same one-way world as cooling tea and fading stars. The psychological arrow of time, the fact that we remember the past and not the future, is built on the thermodynamic arrow. You remember childhood because childhood left traces in your present brain and body, not because the future is less interesting or less polite. Cause and effect also depend on this direction. We are used to saying that causes come before effects. A match is struck, then the flame appears. A stone is thrown, then the window breaks. A hand presses a piano key, then the note sounds. In daily life, this ordering feels so certain that reversing it sounds absurd. The note does not sound first and then force the finger downward. The window does not break and then summon the stone through the air. But causality, as we experience it, depends on records, energy flow, and entropy increase. Effects contain traces of their causes. The broken window contains evidence of the stone. The sound wave carries energy from the piano. The flame spreads heat and light from the match. The universe builds a history by leaving marks, and those marks accumulate in the direction of increasing entropy. There are other arrows of time too, and one of the interesting facts is that they all seem to point in the same direction. There is the thermodynamic arrow linked to entropy. There is the psychological arrow linked to memory and experience. There is the causal arrow linked to causes producing effects. There is also a cosmological arrow linked to the expansion of the universe. Distant galaxies are moving away from one another as space expands. The universe was once hotter, denser, and more uniform. It has grown larger, cooler, and more structured in some places, while the overall entropy has increased. We experience time in a universe that is expanding, cooling, forming stars, aging stars, dispersing radiation, and changing on every scale. The fact that these arrows align is not a trivial detail. It is part of why reality feels coherent. The expansion of the universe gives the story a grand setting. In the early universe, matter and radiation were packed into a hot, dense state. As space expanded, radiation stretched and cooled. Matter gradually gathered under gravity into the first stars and galaxies. That may sound like a move toward order, and locally it was. Gravity produced structures. It pulled gas into dense regions, created stars, and built the cosmic web of galaxies and clusters. But this did not violate the arrow of time. Gravity allowed energy to be released and spread in new ways. Stars shone. Supernovae exploded. Black holes formed. Radiation poured across space. The large-scale story still moved toward greater entropy, even while local islands of structure appeared. The arrow of time is not a rule that every corner must become smoother at every moment. It is a rule about the overall direction of the whole account. This helps with a common misunderstanding. People sometimes think entropy means that complexity should always decrease, so the existence of life, planets, and galaxies seems confusing. But complexity can arise in a universe moving toward higher entropy, because complexity often forms where energy is flowing. A whirlpool can appear as water drains. A flame can hold a shape while fuel burns. A storm can become organized while heat moves through the atmosphere. A living body can remain ordered while food energy is transformed and heat is released. These structures are not standing outside the arrow of time, they are carried by it. They are temporary forms made possible by the movement from useful differences toward less useful distributions. In that sense, the arrow of time does not only describe decay, It also describes the conditions under which temporary order can exist. A useful image is a hill and a valley, though we do not need to imagine anything too dramatic. Water at the top of a hill has the ability to flow downward. Along the way, it may carve channels, turn wheels, make foam, carry leaves, and shape the land. When it reaches a flat basin, the dramatic flow stops. The water still exists, but the difference in height that drove the motion has been spent. Entropy works in a broader way. Differences in temperature, pressure, chemical energy, and gravitational arrangement provide opportunities for action. As those differences are used and spread out, the ability to drive organized change decreases. The arrow of time is the direction in which those opportunities are gradually spent. At the microscopic level, the puzzle remains fascinating. If tiny motions can in principle be reversed, why do large systems behave irreversibly? The answer is again numbers. A few particles can behave in ways that seem flexible and reversible, but a cup of tea, a human body, or a cloud of gas contains enormous numbers of particles. To reverse the cooling of tea, you would need the motions of countless molecules in the room, cup, table, and tea to coordinate so that energy flowed back into the liquid in exactly the right way. Any tiny mismatch would spoil the reversal. Since the spread-out state has so many more possible microscopic arrangements, the system almost always remains in that broad family of states. Large numbers turn probability into certainty for everyday purposes. This is why we can speak confidently about the direction of everyday events, even though the microscopic world is full of random motion. A single molecule might do something surprising. A vast crowd of molecules behave statistically. It is rather like trying to predict one person in a city compared with predicting rush hour traffic. One person may turn down an unexpected street, stop for coffee, or go home early. But the behavior of millions of people creates patterns that can be measured and expected. In thermodynamics, the crowd is so large that the pattern becomes one of the strongest laws we know. Heat spreads, gases mix, friction produces heat, differences fade unless energy is supplied to maintain them. Friction is a particularly ordinary doorway into the arrow of time. Slide a book across a table and it slows down. Its motion is not destroyed, but organized motion is transformed into disorganized microscopic motion in the book and table, the surfaces warm by a tiny amount. The motion that once had a clear direction becomes scattered among countless vibrations. The reverse would require all those microscopic vibrations to coordinate and push the book forward again. We never see that happen naturally. This is entropy in action. Organized energy becomes less organized. The book stopping is not just a mechanical fact, it is a thermodynamic event. Sound works similarly. Clap your hands once, and a pressure wave travels through the air. The sound spreads outward, reflects from walls, fades, and becomes tiny motions and heat in the surroundings. You do not hear the room gather those vibrations back into a single sharp clap between your hands. Light from a lamp spreads through a room and is absorbed by walls, furniture, and skin. It becomes heat. It does not naturally reassemble into the exact beam that left the bulb. Every fading sound, every dimming ripple, every softening warmth is part of the same one-way road. Aging is another expression of this, though it must be treated carefully. Living organisms are not simply passive objects falling apart. They repair themselves constantly. Cells replace damaged parts, correct errors, regulate chemistry, and maintain structure. A young body is not low entropy in a simple isolated sense, because it is part of a much larger environment and energy flow. But over time, damage accumulates. Repair systems become less effective. Molecular errors, cellular changes, and structural wear build up. The body continues to fight for order, but it must do so in the same thermodynamic universe as everything else. Aging is not only entropy, but entropy is part of the background that makes maintenance necessary and imperfect. The one-way road is written into biology too. though biology travels it with remarkable complexity. This one-way road is also why the past feels fixed while the future feels open. The past has left records, and those records constrain what we can honestly say happened. The future has not yet produced records, so we experience it as a space of possibilities. Physics adds nuance to this, especially in relativity and quantum theory, where the nature of time becomes more difficult than common sense suggests. But in the practical world of entropy, the feeling is understandable. A broken bowl on the floor narrows the possible past. It tells us there was once a bowl. There was an impact, an energy spread through sound, heat, and motion. Before the bowl fell, many futures were possible. After it broke, one history had become written into the room. Yet the arrow of time does not mean every system instantly races toward maximum entropy. Many systems remain far from balance for long periods because flows continue. Earth remains active because sunlight keeps arriving and heat keeps leaving. Stars remain stable for millions or billions of years because inward gravity and outward pressure maintain a balance while nuclear fuel is consumed. Galaxies persist because gravity shapes their motion. Living things persist because metabolism maintains internal order. A city at night glows because power plants, grids, fuels, and machines keep energy moving through it. The arrow of time is always present, but it can support long-lasting processes. It does not always look like collapse. Sometimes it looks like steady burning, patient orbiting, slow growth, and the long maintenance of form. This is important for understanding the far future. If entropy gives time its direction, then the ultimate limit of entropy would not mean time itself must stop in a simple clock sense. Rather, it would mean the universe loses the useful contrasts that make events rich, organized, and connected in familiar ways. There may still be microscopic fluctuations. There may still be particles, radiation, and extremely rare events depending on the deepest laws. But the grand arrow would have little left to spend. If everything is close to equilibrium, there is no strong flow from hot to cold, no fresh fuel for stars, no easy way to build and maintain complexity. The one-way road would not end with a signpost. It would fade into a landscape where almost nothing remains to mark progress. That thought can feel unsettling, but it also clarifies why our era is special. We live while the universe is still full of gradients. The sun is hot and space is cold. Earth has seasons, weather, oceans, chemistry, and life. Stars are still forming in some regions. Galaxies still shine. Energy is still concentrated in ways that can produce structure and experience. The arrow of time is not only carrying things away, it is carrying us through the part of cosmic history where complexity is possible. Every sunrise is a thermodynamic event. Every meal is a transfer of energy. Every thought is a pattern of activity maintained by a body that must breathe, eat, and release heat. We are not outside the arrow watching it pass. We are made from processes that depend on it. And this gives the subject a grounded kind of beauty, not because it is sentimental, but because it connects so much. The cooling of tea, the shattering of glass, the fading of sound, the formation of memory, the burning of stars, the expansion of the universe, and the aging of living things are not isolated facts. They are different faces of a shared direction. Entropy does not explain every detail by itself, but it gives the story its slope. It tells us why some events are common and their reverses are not. It tells us why the universe keeps records. It tells us why useful energy matters. It tells us why time feels less like a still map and more like a road we are already travelling. For now, that road remains busy. Stars continue to make the night sky more than darkness. Inside them, matter is transformed, energy is released, and the universe spends some of its stored potential in light. But stars are not permanent lamps. They are long-lived processes, and every process has a fuel, a balance, and an ending. To understand what entropy does on the larger scales, we need to follow those lights forward, past their steady shining, and into the ages when they begin to fade. For now, the road remains bright. Stars still burn across the dark, patient and distant, giving the universe its familiar lights. They are so common in our imagination that it is easy to treat them as permanent features of reality, like lamps nailed to the ceiling of space. But stars are not objects in the simple sense. They are processes. A star is matter caught in a long balance between gravity pulling inward and heat pushing outward. It is a furnace, but not a fire in the ordinary household way. It does not burn wood or coal or anything that needs air. It shines because deep in its core, under enormous pressure and heat, light elements are transformed into heavier ones, and a portion of their stored energy escapes outward. That energy begins as activity in the heart of the star, works its way through layer after layer, and eventually leaves as light, warmth, and particles travelling through space. Every star is a slow release of order, a bright way for the universe to spend a difference. This is where entropy becomes visible in the night sky. A star exists because gravity has gathered gas into a dense sphere, which sounds at first like nature making order out of disorder. A wide cloud becomes a concentrated body, a fog becomes a sun. But the story is not just about matter clumping together. As the cloud collapses, it heats up. It radiates energy away. Once the star ignites, it begins sending energy into space for as long as its fuel allows. The local structure of the star is paid for by a larger spreading of energy. A star is not an exception to entropy. It is one of entropy's grand engines. It holds itself together while giving itself away. The life of a star begins in a cold cloud of gas and dust, often spread across vast regions between existing stars. These clouds may look quiet, but they are not perfectly still. They ripple from shock waves, nearby explosions, turbulence, magnetic fields, and the pull of gravity. In some denser region, gravity begins to win. Matter draws together. The cloud fragments into smaller clumps. Those clumps become hotter as they contract. At the centre of one clump, pressure rises until the conditions become extreme enough for nuclear fusion to begin. Then a star is born. Though born is a very human word for something that happens without a cradle, a name tag, or anyone bringing tiny socks. Once fusion begins, the star enters the long, stable part of its life. Gravity keeps trying to crush it inward. The energy produced in the core pushes outward. For a long time, these influences balance. The star shines steadily, using its available fuel. Our sun is in this stage now. It has been shining for billions of years and will continue for billions more, not because it has escaped entropy, but because it has a large store of usable energy and a slow way of releasing it. The sunlight that warms a morning window is part of this release. It began in a dense core, crossed the interior of the sun, flew through space, reached Earth, and then became warmth in air, water, leaves, stone, skin, and eventually radiation leaving Earth again. The light is lovely, but thermodynamically it is also energy spreading from a hot source into colder surroundings. Stars spend their fuel at different rates, depending mostly on their mass. Small stars are frugal. They burn slowly and can last far longer than the current age of the universe. Massive stars are extravagant. They shine intensely, live quickly, and die dramatically. A massive star is like someone who uses all the candles at dinner because the room looks nicer, while a small red dwarf is the sort of star that would carefully label leftovers and remember where it put the spare batteries. The difference matters because the future of the universe depends on how long stars can keep shining and how often new ones can form. A star like the Sun will eventually run low on hydrogen in its core. When that happens, the balance changes. The core contracts and heats, while the outer layers expand. The star becomes a red giant, swelling enormously compared with its earlier size. Its surface cools in relative terms, but because the surface area becomes so large it can shine brightly. For any planets close by, this is not a gentle retirement plan. Eventually the star sheds its outer layers into space, creating a glowing cloud of gas, while the core remains behind as a white dwarf. A white dwarf is not a normal star anymore. It no longer produces energy through fusion in the same steady way. It is a hot remnant, dense and compact, shining mostly because it still has heat left from its earlier life. Over immense time, it cools and fades. That cooling is entropy again, quiet and patient. The white dwarf begins as a hot object in colder space. It radiates, its heat spreads outward, it becomes dimmer. The process takes so long that the oldest white dwarfs in the universe have not yet had time to become completely cold. The universe is still too young for that final stage. But if the future continues long enough, white dwarfs should fade into cold dark remnants sometimes called black dwarfs. No black dwarfs are expected to exist yet, not because physics is waiting for permission, but because there has not been enough time. Some endings require a universe with a very long attention span. More massive stars end differently. When they exhaust the fuel that supports them, their cores can collapse suddenly. The outer layers rebound and explode as a supernova, one of the most energetic events in the universe. For a time, a single dying star can outshine an entire galaxy. These explosions are violent, but they are also creative in a physical sense. They scatter heavy elements into space, including elements needed for rocky planets, oceans, atmospheres, and living bodies. The calcium in bones, the iron in blood, the oxygen in water, and many other elements were forged in stars or distributed by stellar death. A supernova is entropy increasing in a spectacular form, but it is also how the universe enriches the material from which later complexity can arise. After such an explosion, the collapsed core may become a neutron star or a black hole. A neutron star is incredibly dense, made from matter crushed beyond ordinary atomic structure. It can spin rapidly, carry intense magnetic fields, and send beams of radiation into space. It is one of the strangest objects nature makes without technically asking anyone if they were ready. A black hole is stranger still. If the collapsing core is massive enough, gravity becomes so intense that a boundary forms beyond which light cannot escape. From outside, the black hole is dark, not because nothing is happening, but because whatever crosses that boundary cannot send a signal back out in the usual way. It's a place where gravity has become extreme enough to remove matter and light from ordinary communication with the rest of the universe. Black holes might seem like the opposite of entropy spreading. They gather matter into the most concentrated state we know. They swallow gas, stars, dust, and radiation. They can sit at the centers of galaxies, shaping the motion of stars around them. When matter falls toward a black hole, it often forms a hot disk, heating through friction and gravity before crossing the boundary. These disks can shine fiercely, sometimes producing jets that launch particles across enormous distances. So even before matter disappears from view, the process of falling in can release huge amounts of energy into space. Again, gravity gathers, and gathering becomes a way to disperse energy. Modern physics gives black holes an even deeper connection to entropy. A black hole is not merely an empty drain in space. It has properties that behave thermodynamically. It has a kind of temperature, though for large black holes that temperature is extremely low. It has entropy, and not just a little. A black hole's entropy is enormous, larger than the entropy of ordinary matter that formed it. This was one of the great surprises of 20th century physics. It suggested that gravity, quantum theory, and thermodynamics are tied together in ways we still do not fully understand. A black hole hides information from the outside world, and its boundary seems to carry a deep measure of how many states are possible. The details are difficult, but the broad point is clear. When the universe makes black holes, entropy has not gone away. It has found one of its most extreme expressions. Over the ages, galaxies continue to change. New stars form from gas clouds, but the supply of useful gas is not endless. Some gas becomes locked in long-lived stars. Some is blown out by supernovae and energetic black hole activity. Some becomes too hot or too diffuse to collapse easily. As the universe expands, galaxies move farther apart on the larger scales, and fresh interactions become less common in many regions. Star formation slows. The bright blue stars, which live fast and die young, disappear first because they use their fuel quickly. Smaller red stars remain for far longer, glowing faintly and steadily. In the far future, the universe becomes less like a grand fireworks display and more like a room where most of the candles have already burned down, leaving only a few small embers tucked here and there in the dark. Those small red stars may become the last ordinary stars. Because they burn fuel slowly, they can shine for immense spans of time, far beyond the current age of the universe. Around them, planets may continue to orbit. Some might remain warm enough for chemistry, perhaps even life, though we should speak carefully because this is far beyond what we know. Eventually, even the smallest stars will use up their fuel. They will fade into remnants. The era of starlight will end not with one great switch being flipped, but by a gradual dimming. Star after star will leave the main stage. Galaxies will grow darker. The universe will still contain matter, but less of it will be arranged in ways that produce fresh light. The end of star formation is crucial for the entropy story. Stars are sources of usable energy because they maintain strong differences. Their cores are hot, space is cold, they release energy outward. Planets can intercept a little of that energy and develop complex surface processes. When stars are gone, a major source of energy flow disappears. There may still be other processes, but the familiar cosmic engine of light and warmth is mostly finished. The universe moves deeper into an age of remnants. White dwarfs cool, neutron stars drift, black holes remain. Planets, if still bound to anything, grow cold and dark. Some objects collide, some are ejected from galaxies by gravitational interactions, some fall into black holes. Over enough time, even galaxies themselves become less like shining cities and more like loose collections of dark leftovers moving through expanding space. This long future is not empty at first, it is simply dim. There may be brown dwarfs, failed stars too small to ignite steady fusion. There may be planets without suns, wandering through interstellar darkness. There may be cold stellar remnants and faint radiation. There may be black holes of many sizes, from those formed by dead stars to the enormous ones at galactic centers. If two black holes meet, they can merge, releasing gravitational waves that ripple through space. These waves carry energy outward, another form of spreading. Over very long periods, matter that remains in galaxies may gradually be swallowed by central black holes or scattered into intergalactic space. The universe becomes less organized around shining matter and more dominated by dark compact objects and faint leftovers. One of the quiet facts about black holes is that they are not truly eternal, at least according to the best theory we have that combines aspects of quantum physics with curved space. They should slowly emit radiation. This process is extraordinarily weak for large black holes. A black hole with the mass of a star would take a span of time so vast that ordinary cosmic history seems brief beside it. Supermassive black holes would last even longer, but if nothing interrupts them, they would gradually lose mass and eventually evaporate. This is not evaporation like steam rising from a kettle. It is a quantum process associated with the boundary of the black hole, and it becomes important only across almost unimaginable times. Still, it means that even black holes may not be final permanent objects. They too may fade. When a black hole evaporates, its energy spreads into radiation. At the very end, depending on the details of physics not yet fully settled, there may be a final release. But for most of its lifetime, the process is slow beyond comprehension. A black hole is like the universe putting a great deal of entropy into a very dark account and then withdrawing it one faint particle at a time. That image is not exact, but it gives the feeling. Black holes are the last major reservoirs of energy and entropy in many visions of the far future. After stars fade, after ordinary matter grows cold, black holes may dominate the remaining story. They are the long afterglow of gravity. There is also the question of matter itself. Some theories suggest that protons, the particles found in atomic nuclei, may eventually decay over enormous timescales. This has never been observed, and it may not happen. Experiments have placed strong limits on it, but the possibility remains in certain grand theories. If protons do decay, then ordinary matter as we know it would not last forever. Planets, rocks, dust, and stellar remnants would slowly dissolve into lighter particles and radiation. If protons do not decay, matter could remain in some cold forms for far longer, perhaps undergoing rare changes through other processes. Either way, the broad thermodynamic direction continues. Structures become less able to support active change. Energy becomes more thinly distributed. The universe grows quieter. It is worth pausing on how different this future is from the dramatic endings often imagined in stories. There is no need for the universe to explode in a final fire or collapse into a single instant of destruction, at least not in the most widely discussed heat-death picture. Instead, the ending is slow fading, stars exhaust fuel, remnants cool, black holes absorb and later radiate, space expands, the distance between active regions grows, the usable differences that made complexity common become rare. The universe does not crash, it relaxes. If that sounds almost too calm, that is part of what makes entropy so strange. The most profound ending may not be loud. It may be the loss of reasons for anything loud to happen. And yet, during the long fading, gravity keeps adding texture to the story. Galaxies may merge before they grow dark. Stars can be flung into deep space. Remnants can collide. Black holes can spiral together. Even in a universe where star formation declines, there can be rare flashes, mergers, impacts, and gravitational events. The road toward maximum entropy is not perfectly smooth. It has late sparks. It has leftovers interacting in the dark. But these events become less frequent as time stretches onward. The universe becomes more dilute, more separated, more settled. Each event spends another difference. Each glow fades into a wider cold. The contrast with our present era could hardly be stronger. We live while stars are common. The Milky Way is still bright with them. The sun is stable enough to give Earth long ages of warmth. Heavy elements are available because earlier generations of stars lived and died. Chemistry is rich. Energy flows are strong. Life has had time to arise and become complex. This is not the beginning of the universe, and it is not the end. It is a middle age filled with light. Perhaps not the only age where observers can exist, but certainly an age where the conditions are generous. To ask what happens when stars fade is also to recognize how much we owe to the fact that they have not faded yet. The night sky can make stars seem timeless because human lives are brief. A constellation looks almost the same from one generation to the next, though careful measurement shows motion. Ancient observers saw many of the same bright stars we see. It is natural to think of them as fixed. But physics tells us that every star is temporary. Some are young, some are middle-aged, some are already dead but still visible to us because their light has been travelling for years, centuries, or longer. Looking into space is also looking into time, and much of what we see is part of a process already changing. A star in the sky is not a dot. It is a life cycle at a distance. The fading of stars also changes the meaning of darkness. Darkness is not simply the absence of light in a room after the lamp is switched off. Cosmic darkness in the far future is the result of fuel spent across enormous scales. It is what remains when fusion no longer lights the ordinary universe, when warm planets no longer receive steady sunlight, when galaxies no longer glow with fresh stars. The universe may still contain particles and radiation, but the kind of darkness that follows the stellar era is deeper than night. Night on Earth is temporary because the planet turns and morning comes. The later darkness of the cosmos would not wait for sunrise. Still, black holes remain, and they give the universe a strange late structure. A black hole does not shine like a star, but it has mass, gravity, and thermodynamic significance. Around it, if matter is still available, there can be activity. But once surrounding matter is gone or swallowed, the black hole becomes quiet. Its long future is governed by extremely slow radiation. This makes black holes both endings and transitions. They are endings for stars, gas, and matter that fall into them. They are also part of the long path by which concentrated energy eventually returns to the universe in a more spread out form. They do not defeat entropy, they deepen it. If we follow the story far enough, the universe after stars becomes a place where most familiar categories lose their usefulness. There are no ordinary days without suns rising over planets. There are no seasons without stars and orbital warmth. There is no weather on frozen worlds in the way we know it. There are no ecosystems powered by sunlight unless some rare alternative energy source persists. Time may still be measured by changes, but changes become sparse. A clock could tick if a clock somehow survived, but the cosmic environment would offer little of the rich activity that once gave time its texture. The arrow of time would still point toward increasing entropy, but the road would be emptier. This does not mean nothing can ever happen. Rare events may remain possible. Particles may interact. Black holes may evaporate. Quantum processes may produce tiny fluctuations. But compared with the bright age of stars, the universe becomes profoundly inactive. The main story is no longer formation, burning, and renewal. It is cooling, isolation, and dispersal. When we say stars fade and black holes remain, we are describing the transition from a universe powered by stellar furnaces to one ruled by remnants and long waiting. There is a human temptation to hear this as sadness, but the scientific point is clearer and more useful than sadness. Stars fade because they shine. They end because they have spent energy making light, elements, planets, and possibilities. Black holes remain because gravity gathers what is left into extreme forms, and even those forms are part of the same thermodynamic account. The fading is not a mistake in the universe. It is the consequence of the same laws that allowed stars to exist in the first place. A star cannot warm a planet without using fuel. It cannot make heavy elements without changing its internal state. It cannot give light without releasing energy into space. The ending is built into the shining. That is why the story of entropy is not separate from the story of beauty or complexity. The universe can make stars because there are gradients to spend. It can make planets because stars live and die. It can make chemistry because elements are forged and scattered. It can make life because a warm star shines into cold space and a planet receives a narrow stream of that energy. But every one of these gifts belongs to a process with direction. The same arrow that allows light to flow also ensures that the source will not burn forever. As we move from the age of stars into the age of remnants, the question becomes more focused. If the great lights go out, if black holes slowly take over the thermodynamic story, and if even they eventually fade, what kind of universe is left? This brings us closer to the idea often called heat death, the state where entropy approaches its limit and usable energy becomes almost impossible to find. The stars have shown us how the universe spends its differences. The next step is to imagine what happens when almost all of those differences have been spent. The stars have shown us how the universe spends its differences slowly, brilliantly, and with more patience than any living thing can really imagine. A star takes matter, gathered by gravity, and turns it into light. A planet takes a little of that light and turns it into weather, chemistry, warmth, and sometimes life. A black hole takes what falls too close and stores it in one of the strangest forms nature allows, then, if the laws we trust continue to hold, gives it back across ages so long that ordinary words begin to feel a little underdressed. All of this is motion along the same road. Energy that was concentrated becomes energy that is spread out. useful differences become less useful. Structure forms, shines, cools, collapses, and fades. So when we finally speak of heat death, we are not suddenly changing the subject. We are following that road to the point where the road becomes almost flat. The phrase heat death sounds dramatic and also slightly misleading. It can make a person imagine the universe ending in fire, as if everything becomes hotter and hotter until space itself is glowing like an overheated oven someone forgot to switch off. But heat death does not mean a final blaze. It does not mean the universe is cooked in any ordinary sense. In fact, the future usually imagined under this name is cold, thin, dark, and spread out. The death in heat death refers to the loss of usable energy differences. The heat part comes from thermodynamics, from the idea that once energy has been distributed as evenly as possible, there is no longer a meaningful way to use temperature differences to drive work. Energy remains, but it is no longer arranged in helpful contrasts. The universe is not empty of energy, it is empty of opportunity. That is the key distinction. A universe at or near maximum entropy still contains something. It may contain radiation, particles, perhaps extremely faint fields, perhaps the last traces of processes we do not yet fully understand. But what it lacks is the kind of difference that makes large-scale events possible. A hot star beside cold space is a difference. A charged battery beside an empty circuit is a difference. A planet with a warm surface and a cold upper atmosphere is a difference. A living cell with carefully maintained chemical gradients is a difference. Heat death is what happens when differences like these are mostly gone. Without differences, energy has nowhere useful to flow. Without flow, there is no engine. Without engines, no stars, no weather, no metabolism, no ordinary computation, no fires, no clocks that can be built and maintained in the familiar way, and no easy way for matter to organize itself into the complicated structures we know. It may help to picture a room that has just had a heater turned off. At first, one part of the room might be warmer than another. The radiator is hot, the window is cool, the air near the ceiling is slightly different from the air near the floor. Heat moves, currents form, surfaces exchange energy. Over time, if the room is isolated enough, the differences soften. Eventually the air, walls, furniture and objects approach the same temperature. At that point the room has not vanished. The air molecules are still moving, the objects still exist. But the useful thermal contrasts have faded. Nothing much can be driven by heat flow inside that room, because there is no strong heat flow left. Heat death is like that idea extended to everything, though of course the universe is not a room, and it is not neatly sealed in the way a box in a laboratory might be. Still, the image gives us the feeling. The universe approaches a state where everything has relaxed as much as it can. The word equilibrium is often used here. Equilibrium means balance, but not balance in the sense of a perfect statue or a peaceful painting. It means a condition where there is no net tendency for large-scale change. Microscopic motion can continue, particles can still move, radiation can still travel. But on the large scale, there are no strong imbalances left to exploit. A glass of water sitting at room temperature is in a kind of thermal equilibrium with the room if they share the same temperature. Molecules still move inside it. They do not freeze into absolute stillness. But the water is not naturally warming the room or cooling it in any noticeable way. It is not driving a machine. It is not producing weather. It is simply sharing the same background condition. In heat death, the universe becomes something like this on the largest possible scale, not perfectly still, but stripped of the unevenness that makes rich change possible. This is why heat death is sometimes described as the universe reaching its maximum entropy. Maximum entropy does not mean every object is broken or every place looks messy in a human sense. It means that, given the conditions of the universe, energy and matter have reached the most probable, most spread out, least useful arrangement available. There are no fresh gradients to tap. A gradient is simply a difference across space or between parts of a system. Temperature gradients, pressure gradients, chemical gradients, gravitational gradients, all of these can drive processes. When the gradients disappear, the processes lose their source. A wind stops when pressure differences fade. A river stops turning a wheel when there is no height difference to carry water downward. A heat engine stops when hot and cold reservoirs become the same temperature. A living body stops when it can no longer maintain the differences that allow its cells to function. A universe in heat death is not necessarily a universe with nothing in it. It is a universe where almost nothing can be done with what remains. The path toward this state is slow because the universe has many stages to pass through. We are living in a bright era, a time when stars still fill galaxies and planets can receive light. But star formation cannot continue forever if the available gas is used up, locked away, heated, dispersed, or swallowed. The large blue stars die first because they burn their fuel rapidly. Smaller stars last much longer, especially the faint red ones, which spend their fuel with extraordinary thrift. Long after stars like the Sun have become remnants, these small stars may still glow, dim and steady, like the final lamps in a vast building after most of the rooms have gone dark. Eventually they too fade. The stellar era winds down, not in one evening, but across timescales so enormous that the current age of the universe is just the opening paragraph. When the last ordinary stars fade, the universe enters darker age of remnants. White dwarfs cool. Neutron stars sit dense and silent unless disturbed. Brown dwarfs drift. Planets, asteroids, dust, and frozen debris continue moving through space. But without steady starlight, most of them are cold and inactive. Galaxies, if they still hold together locally, become collections of dark objects rather than shining spirals and glowing clouds. Some remnants may collide now and then. A brown dwarf might merge with another and briefly ignite some process. A star remnant might pass too close to a black hole. Rare events can still happen. But rare is the important word. The universe becomes less like a crowded harbour and more like a dark ocean with a few drifting objects separated by distances that grow harder and harder to comprehend. Black holes then take on a major role in the far future. They are the great survivors of the post-stellar universe. Some are born from massive stars. Others sit at the centres of galaxies containing millions or billions of times the mass of the Sun. They can merge and grow. They can swallow matter that comes too close. In the deep future, much of the remaining matter in bound regions may eventually be ejected into intergalactic space or captured by black holes. The universe becomes dominated by these dark gravitational remnants, not because they are alive or purposeful, but because they are hard to destroy and very slow to change. They are the heavy punctuation marks near the end of the visible cosmic story. Yet even black holes are not expected to last forever. According to a major insight connecting quantum theory and curved space, black holes should emit a very faint kind of radiation. For black holes of ordinary stellar mass, this radiation is so weak that it is completely overwhelmed by the environment today. For supermassive black holes, the process is slower still, but in the far future, after stars are gone and the universe is colder and emptier, this faint emission becomes the way black holes gradually lose mass. They shrink across spans of time so vast that the word slow barely feels adequate. Eventually, if this picture is right, they evaporate away, returning their mass as thin radiation into the universe. The darkest objects become, in the end, another route by which energy spreads. After the black holes fade, the universe is in a condition much closer to heat death. What remains depends on details that physics has not fully settled. If ordinary matter is unstable over extreme time, then the protons inside atoms may eventually decay, leaving radiation and lighter particles. If protons are stable, then some cold remnants of matter may last far longer, perhaps altered by rare quantum processes. Either way, the broad thermodynamic picture remains. The universe becomes dilute, cold, and close to equilibrium. There are few or no large structures with usable energy flows. the background radiation becomes stretched by expansion. Particles are separated by immense distances. Events become rare. The clock of the universe, if we may speak that way, still has ticks available in principle, but almost nothing remains to count them. Expansion is central to the story. Observations suggest that the expansion of the universe is accelerating, driven by what we call dark energy, though the true nature of dark energy remains one of the great mysteries. If this acceleration continues, distant galaxies will move beyond one another's reachable horizons. Future observers, if any could exist far enough along, might see only their own local region, with the rest of the cosmos carried beyond view. Over even longer times, as stars fade and matter thins, expansion helps isolate what remains. Space does not expand inside small bound systems in the simple way it expands between distant galaxies, but across cosmic distances it steadily stretches the stage. Light travelling through this expanding space loses energy. Radiation becomes colder and longer in wavelength. The universe not only uses up its bright sources, it also stretches their leftovers until they become less and less significant. This is one of the reasons heat death feels so final. In earlier stages, when energy spreads, it can still create structure along the way. A star forms, a planet warms, a storm builds, a cell grows. But near maximum entropy, there are no strong flows left to build new patterns. The great circulation of usable energy has run down. There is no fresh sunlight in the ordinary sense, no dense gas cloud collapsing into a new generation of stars, no hot young galaxies bursting with formation. The universe becomes a place where energy is too evenly diluted or too inaccessible to do much. It is not that the laws of physics stop, it is that the conditions no longer support the kind of activity those laws once produced. This is where the phrase, when the universe reaches its limit, becomes important. The limit is not a wall at the edge of space. It is not a final border that matter bumps into. It is a limit of usefulness, a limit of thermodynamic possibility. In everyday life, we understand this intuitively. A battery that is fully drained still contains atoms and energy, but it can no longer power the device. A cup of coffee at room temperature still contains thermal energy, but it cannot warm your hands in the same way. A wound spring that has unwound is still made of metal, but it no longer drives the clock. Heat death is the cosmic version of the drained battery, except the battery is everything, and there is no outside charger waiting politely in a drawer. A natural question is whether this means time ends. The answer is subtle. Heat death does not necessarily mean time stops existing in a physical sense. If there are still particles, radiation, quantum fields and fluctuations, then change of some kind may still occur. But time as we experience it is tied to change, records, energy flow, and the creation of new states that can be distinguished from old ones. In a universe near equilibrium, meaningful change becomes scarce. Without large-scale processes, there are few new records. Without records, there is little history in the ordinary sense. A clock could only function if it had a source of usable energy and a way to maintain its internal differences. Near heat death, such conditions become extraordinarily difficult. So time may not end, but it becomes thin in a practical sense. It loses the busy texture we associate with days, seasons, life, and memory. There is another subtlety. Maximum entropy in an expanding universe is not as simple as maximum entropy in a sealed box. A box has fixed walls and a fixed volume. The universe, as far as we can tell, is not a box with walls. Space itself expands, and that expansion changes what states are available over time. Gravity also makes entropy more complicated than it is for gas in a container. A uniform gas in a box is high entropy under ordinary conditions, but in a universe with gravity, clumping can increase entropy, because gravitational collapse releases energy and can form black holes with enormous entropy. This is why the early universe can be described as low entropy, even though it was hot and fairly uniform. Its smoothness was special in a gravitational sense. The later formation of galaxies, stars and black holes was part of entropy increasing. So heat death in cosmology is not just everything becoming a smooth gas, it is the result of expansion, gravitational evolution, radiation, black holes, and the gradual exhaustion of ways to create useful differences. If that sounds complicated, it should. The universe is not a tidy classroom example. It does not sit still while we draw neat diagrams and ask it to behave, but the broad direction remains understandable. Useful energy becomes less available, stars stop forming, existing stars fade, remnants cool, black holes dominate and then evaporate, radiation thins, matter, if unstable, decays. Differences become too weak or too isolated to support complexity. The universe approaches a condition where entropy is as high as it can effectively become under its circumstances. That is heat death. This future is sometimes described as bleak, and from a human point of view it certainly lacks many comforts. There are no warm kitchens in the ordinary picture, no oceans shining under a sun, no forest turning light into sugar, no voices in the evening, no small domestic arguments about who left the cup on the table. But it is important not to mistake emotional reaction for scientific meaning. Heat death is not a punishment. It is not the universe failing. It is what follows from the same laws that allow stars, planets, and life to exist in the first place. The flow of energy from concentrated to spread out forms is what makes the present active. The fact that this flow cannot continue forever is the other side of the same truth. There is a strange humility in this. We live in a universe that is not at its limit. That may sound obvious, but it is profound. There are still gradients everywhere. The sun is far hotter than space. Earth has a warm surface and a cold upper atmosphere. Cells maintain chemical differences. The brain maintains electrical and chemical patterns. Civilization uses stored and flowing energy in countless ways. Every meaningful action depends on the universe not yet being in equilibrium. You can move your hand because your body has usable energy. A tree can grow because sunlight arrives. A cloud can rain because heat has moved water through air. A star can shine because gravity and nuclear processes hold a powerful imbalance. We are creatures of an unfinished thermodynamic story. Heat death also gives us a clearer sense of what life is. Life is not just matter arranged in a clever way. It is matter arranged in a clever way while energy flows through it. A living thing must stay far from equilibrium. It must keep some things inside and others outside. It must maintain boundaries, repair damage, regulate temperature, manage chemistry, and release waste. When a living thing reaches equilibrium with its environment in the wrong way, life has ended. The body may still contain energy and atoms, but the organized flows that maintained it are gone. In this sense, all life exists by delaying local equilibrium through the use of energy, while increasing entropy overall. Life is a temporary standing wave in the river of thermodynamics. Civilizations are similar, though on another scale. A city glows because energy is being directed. Food is grown, transported, stored, and eaten. Water is pumped. Buildings are heated or cooled. Information is processed. Waste heat is released. Materials are repaired and replaced. A city without energy flow becomes still. A civilization without energy gradients cannot continue its activities. This does not mean the distant future of heat death tells us what to do tomorrow in any simple moral sense, but it does remind us that every structure, from a cell to a society, depends on flows it does not own forever. Maintenance is not a side activity, it is the activity. The far future also raises the question of whether anything could survive or continue near heat death by using tiny remaining differences. Some speculative ideas imagine advanced civilizations finding ways to extract energy from black holes, from cosmic expansion, from extremely cold environments, or from processes we do not yet know how to use. Physics does not invite us to rule out every clever possibility too quickly, but the larger trend is difficult to escape. As the universe expands and equilibrates, energy becomes more diluted, more inaccessible, and less able to support organized systems. Even the most patient intelligence would face limits if there are no gradients left to harvest. The question becomes not merely how efficient a system can be, but whether there remains anything available to be efficient with. Could fluctuations disturb the stillness? In statistical physics, even systems at equilibrium can have fluctuations. Tiny local deviations may occur. On extremely long timescales, very rare events might be possible. Some discussions of the far future involve strange possibilities, including small temporary decreases in entropy or freak arrangements arising from random fluctuations. But these ideas belong to a realm so far beyond ordinary timescales that they are difficult to connect with familiar existence. They do not restore the bright universe of stars and planets in any practical sense. They suggest that equilibrium may not mean absolute nothingness, but rather a condition where meaningful ordered events are fantastically rare and limited. The universe near heat death is not lively simply because a rare twitch may be possible. This distinction matters because heat death is not a sudden moment when a cosmic bell rings and everything declares itself finished. It is an approach. Entropy increases. The universe moves closer to equilibrium. Processes become slower, rarer, and less energetic. There may not be a final instant that can be pointed to as the exact arrival. It is more like a sound fading until it becomes impossible to distinguish from silence. At first, the melody is clear. Then only a few notes remain. Then a faint vibration. Then perhaps nothing that any observer could use as music. Heat death is the fading of cosmic music, not the smashing of the instrument. And yet, talking about this ending while sitting in the bright middle of the universe changes the way the present looks. A lamp becomes a thermodynamic event. A breath becomes a maintained imbalance. A sleeping body becomes a quiet miracle of regulation. The night sky becomes not just decoration, but evidence of a universe still rich with usable differences. Even the act of listening to a long explanation depends on energy moving through circuits, speakers, air, ears, nerves, and brain. Heat death is distant beyond imagination, but the principles that point toward it are here in every warm object cooling, every battery draining, every candle burning, every star giving itself to space. So when we say heat death is the universe reaching its limit, we mean that the universe reaches the limit of what entropy allows once almost all useful differences have been spent. It is the long outcome of energy spreading, gravity gathering and releasing, stars burning, black holes storing and evaporating, and expansion thinning the remains. It is not a fiery end, not a dramatic collapse, and not necessarily absolute nothingness. It is a future of near balance, where the ingredients of activity remain only in forms too scattered or too equalized to build much from them. The universe becomes quiet because it has run out of contrast. From that quiet, the next question is almost unavoidable. If heat death is not exactly nothing, and if some kind of time or fluctuation may still remain, what happens after the universe can no longer do anything in the ordinary sense? What does after even mean when there are no stars to mark eras, no clocks to keep rhythm, no observers to remember a before, and no strong differences left to turn possibility into events? What does it mean to ask what happens after nothing can happen? At first, the question sounds like a trick, the kind of sentence that wanders into the room wearing slippers and refuses to explain itself. If nothing can happen, then surely there is no after, no event, no story, no clock on the wall quietly insisting that something is still moving along. But physics is often most interesting precisely where ordinary language begins to wobble. Heat death does not necessarily mean absolute nothingness. It means the universe has reached, or has come very close to, a state where there are no useful differences left to drive the kinds of processes we understand. There may still be particles, there may still be faint radiation, there may still be space, fields, gravity in some form, and the strange, restless background of quantum physics. But the familiar engines of change are gone. There are no stars turning fuel into light, no planets warmed by steady suns, no weather rolling across skies, no chemistry constantly refreshed by incoming energy, no living systems maintaining themselves far from equilibrium. The universe is not necessarily absent, it is simply unable in the ordinary sense to do very much. This is one of the strangest shifts in the whole story. We're used to thinking of existence and happening as almost the same thing. A thing exists, and therefore it does something. A candle flickers, a body breathes, a river flows, a star shines. Even a stone, quiet as it seems, warms in sunlight, cools at night, gathers frost, wears down under rain, and participates in the world around it. But a universe near maximum entropy challenges that habit. Something may exist without producing a meaningful sequence of events. Matter and energy may remain, but without strong gradients there is no useful flow. Without flow there is no natural machinery. Without machinery there is no building, repairing, remembering, growing, burning, or waking up and wondering why the alarm sounds personally offended. So when we say nothing can happen, we have to be careful. We do not mean that every microscopic motion has stopped in a simple frozen way. At ordinary temperatures, particles move. At extremely low energies, quantum fields still have their own subtle behaviour. Even empty space in modern physics is not quite the same as philosophical nothing. It may have structure, fluctuations, and rules. The statement is more about meaningful macroscopic events. A universe after heat death has no easy way to concentrate energy into a star, no natural way to gather scattered heat into a useful engine, no steady source that could support the complex cycles required for life or thought. There is still physics, but there may be very little history. History needs differences. To tell any story, something must be one way and then another. A match is unlit and then lit. A star is forming and then shining. A child is young and then older. A signal is sent and then received. In every case, a record is created, and creating a record requires physical change. If the universe becomes too close to equilibrium, the creation of new records becomes rare or impossible on large scales. The past might still be described by some ideal external account if such a view made sense, but inside the universe there would be almost nothing left to mark a before and after. Without clocks, observers, or processes capable of leaving traces, time becomes less like a road with milestones, and more like an empty plain where distance is hard to notice. This does not mean time itself is proven to vanish. That is a deeper question, and different theories treat it differently. In everyday physics, time is a parameter we use to describe change. In relativity, time is woven with space and depends on motion and gravity. In thermodynamics, time has direction, because entropy tends to increase. Near heat death, entropy has little room left to increase in any familiar way. The thermodynamic arrow becomes weak, not because it reverses, but because there are so few processes left to reveal it. If nothing important changes, then asking how much time has passed begins to lose practical meaning. A clock that cannot be powered, repaired, read, or compared with anything is not much of a clock. It might still have a theoretical duration assigned to it, but there is no living experience of that duration, no diary of the darkness, no tired observer saying that eternity is starting to feel a bit excessive. The idea of after becomes especially difficult here. In ordinary life, after means the next event in a sequence. After sunset comes night, after winter comes spring. After a star exhausts its fuel comes a remnant. But after heat death, there may be no regular sequence of meaningful cosmic stages. There may be no new era in the sense of a rich set of processes taking over from the old one. The universe does not necessarily enter a dramatic new phase with a fresh cast of characters. It may simply continue in a nearly exhausted state. If an event occurs, It may be so rare, so small, or so isolated that it does not form part of a larger pattern. This is hard to picture because our minds are built for environments where change is constant. We live among cycles, day and night, hunger and eating, work and rest, breath in and breath out. We are made of rhythms, so a universe without usable rhythm feels nearly impossible to imagine. One way to approach it is to think of a machine that has wound down. Suppose you have an old mechanical clock. While it is wound, energy stored in its spring is released gradually through gears, letting the hands move in a regular way. The clock is not just metal, it is metal plus stored difference plus controlled release. Once the spring is fully unwound, the clock still exists. Its parts are still there. It may still be beautiful on the shelf, but it no longer ticks unless energy is put back into it. The future of heat death is like a clock for which there is no outside hand to wean the spring. The universe contains the parts, but the stored differences that made large-scale motion possible have been spent. A drained battery gives the same lesson in modern clothing. The battery is not gone when it is empty. It has mass, it has atoms, it has internal structure. But the chemical separation that allowed it to deliver electrical energy has been reduced. The phone does not care that the battery still contains energy in the broad physical sense. It needs energy in the right arrangement. It needs a useful difference. Heat death is the universe with its useful differences drained away, not destroyed, not erased, spread out beyond practical recovery. If there were an outside to the universe, one might imagine recharging it. Add fresh low entropy energy, compress matter, create a new hot region beside a cold one, start another round of stars. But the universe, as physics usually treats it, is not a device sitting in a larger workshop. There is no known external socket. No cosmic technician arrives with a clipboard and says the whole thing needs a reboot. We can speculate about larger frameworks, multiverses, cycles, or unknown physics, but within the standard heat-death picture, the universe must work with what it has. Once the usable gradients are gone, there is no ordinary way back. This is why heat death feels different from many other endings. A forest fire ends, but new growth may follow because sunlight, soil chemistry, water, and living systems remain. A winter ends because Earth continues orbiting a star. A civilization may collapse, but the planet still has energy flows and materials that other systems can use. Even a star dying enriches space with elements that may later form new stars and planets. These are endings inside a larger active universe. Heat death is the fading of the larger active universe itself. It is not a local ending, it is the loss of the conditions that make ordinary renewal possible. There may still be isolated changes. A particle might decay if it is unstable. A photon might travel through expanding space. A black hole, if any remain in a given stage of the story, might slowly radiate. But after the black hole era has also faded, the remaining universe becomes more difficult to describe in familiar terms. It may contain extremely low energy radiation stretched to enormous wavelengths. It may contain light particles separated by vast distances. It may contain whatever stable particles nature permits. If dark energy remains as a constant feature of space, the expansion may continue, increasing the separation between whatever remains. The universe becomes not only quiet, but also increasingly disconnected. Regions drift beyond contact. Even the possibility of gathering scattered pieces becomes less realistic as space itself expands. Communication depends on signals. Signals depend on energy. Meaningful communication depends on a sender, a receiver, and a shared physical context where the signal can be created, transmitted, and interpreted. In the far future near heat death, all of these requirements become unavailable. There are no functioning transmitters, no receivers, no stable environments where information can be stored and protected. The universe may still obey laws, but there is no one and nothing organized enough to make use of those laws in the way observers do. This is a hard thought, because observation feels central to us. But the universe spent most of its early history without human observers, and in this future it may spend vastly longer without any observers at all. Physics does not require an audience, even if we are rather attached to having one. Information itself becomes a subtle question. In many areas of physics, information is not supposed to simply vanish. The exact state of a system may evolve according to rules that preserve information in some deep sense. But useful information is another matter. A library that has burned may, in principle, have its information dispersed into smoke, heat, ash, and light. But no reader can use it as a library. The information has become scrambled beyond practical recovery. In a heat-death universe, the information about earlier stars, planets, and lives may be dispersed in the total physical state, but not stored in accessible records. The difference between existing in principle and being recoverable in practice becomes enormous. A memory that cannot be read, a record that cannot be found, and a message scattered into unreachable radiation are not useful to any future process. This is where entropy and information meet in a way that feels almost personal. Our lives depend on making and preserving low-entropy records. A notebook, a hard drive, a brain, a carved inscription all keep some pattern stable enough to connect one moment to another. But preserving a record requires protection from noise, damage, heat, decay, and dispersal. It requires energy and structure. In the far future, the universe no longer provides friendly conditions for preservation. Records fade, decay, scatter, or fall into black holes long before the final quiet. Once all organized record-keeping is gone, the universe may still carry the consequences of its past in a deep physical sense, but not in a narrative sense. The story has no pages left that anything can turn. The absence of meaningful events also changes how we think about space. In the universe we know, space is full of relationships. A planet orbits a star. A moon orbits a planet. Gas falls into galaxies. Light travels between sources and observers. Distances matter because things can interact across them. Near heat death, with particles separated by vast distances and expansion carrying regions apart, space becomes less relational in the ordinary sense. A distance between two things matters less if they can never influence one another again. The universe may become a collection of isolated remnants, or radiation spread through an expanding background, with fewer and fewer meaningful interactions. Space remains, but the relationships that made it active are mostly gone. It is tempting to ask whether a new universe could somehow begin from this state. Some speculative ideas suggest possibilities. Perhaps a rare fluctuation could produce a small region of lower entropy. Perhaps a deeper theory of quantum gravity allows a transition to a new expanding region. Perhaps our universe is one phase in a broader process we do not yet understand. These ideas are fascinating, but they are not settled. They belong at the edge of known physics, where imagination and mathematics explore territory that evidence has not yet fully mapped. The standard heat-death picture does not include an automatic restart. It does not say that once nothing can happen, everything begins again. It says that without usable energy differences, there is no ordinary mechanism for renewal. Even the word nothing needs care. Philosophical nothing would mean no space, no time, no fields, no laws, no possibility. That is not what heat death describes. Heat death is not the universe becoming absolute nothing. It is the universe becoming thermodynamically exhausted. There is a great difference between no ingredients and ingredients that can no longer cook anything. A kitchen with flour, water, sugar, and heat can make bread. A kitchen with the same ingredients scattered across the floor, cooled to the same temperature, and no working oven is another matter. The ingredients remain, but the process is gone. The heat-death universe is not pure absence. It is a condition of almost total impracticality. This is one of the reasons the idea is scientifically useful. It teaches us that the ability to do work depends on arrangement, not just existence. Energy must be organized in a way that allows flow. Matter must be structured in a way that allows interaction. Information must be stored in a way that resists dispersal. Life must be maintained away from equilibrium. A universe after nothing can happen shows the difference between having energy and having usable energy, between having time and having meaningful change, between having physical state and having history. The emotional weight of the idea comes from scale. In daily life, when nothing can happen in one place, we move elsewhere. A dead battery can be charged, a cold cup can be replaced, a quiet room can be opened to the street, a tired person can sleep and wake. We are surrounded by reserves and cycles. The far future removes the elsewhere. It imagines a cosmos where every reachable place has also run down, where no fresh source remains over the horizon, where the background itself offers no useful contrast. It is not claustrophobic, because space may be vast beyond measure. It is the opposite, an emptiness so open that almost nothing meets anything else. Yet there is another way to hold this thought without turning it into simple despair. The fact that such a future is possible, or even likely under current understanding, tells us something remarkable about the present. We are not in that state. The universe around us is wildly unfinished. It has gradients everywhere. It has stars and planets, chemistry and light, motion and memory. The difference between the present and heat death is the difference that makes everything we know possible. Every ordinary moment is happening because the universe is still far from equilibrium. The cup cools because the room is cooler. The body lives because food contains usable chemical energy. The eye sees because photons arrive with information. The brain thinks because it maintains delicate electrical and chemical differences. We are not merely living before an ending. We are living inside the conditions that ending has not yet erased. This makes the present less ordinary. A warm hand, a glowing screen, a plant near a window, a dog sleeping on a rug, the sound of distant traffic, all are signs of active thermodynamics. They are evidence that the universe is still able to make and maintain patterns. Even boredom, that famously slow-moving creature, requires a working brain using energy to notice that not enough interesting things are happening. In a true heat-death state, there would be no boredom, because boredom requires someone to be there, comparing one moment with another and feeling that the comparison could be improved. What happens after nothing can happen then may be less like a new event and more like continuation without drama. The universe remains in a state where the usual sources of change are exhausted. If time continues, it does so without much to mark it. If space expands, it does so into a future with fewer relationships. If particles persist, they do so with fewer interactions. If fluctuations occur, they are rare whispers against an immense background. The story does not end with a period so much as it loses the conditions for sentences. Still, physics leaves small doors open, and those doors lead us toward the next part of the journey. Equilibrium does not always mean absolute sameness at every tiny scale. In statistical systems, fluctuations can occur. Usually they are small, usually they fade. In a universe old enough and vast enough, the question of rare fluctuations becomes strange and important. Could tiny pockets of order appear by chance? Could a brief local decrease in entropy happen in an almost empty eternity? Could the future contain rare sparks, not as a return to the bright universe, but as momentary disturbances in the long quiet? To understand that, we have to listen very closely to what almost nothing may still be allowed to do. To understand tiny fluctuations in an almost empty eternity, we have to begin with a very ordinary fact. Stillness is rarely as still as it looks. A quiet room at night may seem motionless, especially when the lights are low and the rest of the house is settled. But the air is full of moving molecules. Warmth is passing through walls, furniture, blankets, and skin. Dust is drifting in currents too slow to notice. Inside every object, atoms are vibrating. Inside your body, cells are working, blood is moving, nerves are sending signals, and chemistry is going about its business with no concern at all for whether anyone is trying to relax. The world can look calm from the outside while remaining restless underneath. Physics is very good at noticing that hidden restlessness. A universe near heat death would be calm in a much deeper way than a quiet room. It would not simply be a place where the lights are off. It would be a universe where almost all usable energy differences have faded. No bright stars, no warm planets under steady sunlight, no great clouds of gas collapsing into new suns, no active galaxies filled with fresh formation, no black holes left to dominate the story if we're imagining a time after even they have slowly radiated away. What remains may be incredibly thin radiation, isolated particles, faint fields, and the enormous expanding background of space. Yet even there, the question remains, is it perfectly still or only almost still? In physics, almost can matter. A fluctuation is a small departure from an average condition. If you watch the surface of a pond on a windless day, it may appear smooth, but tiny ripples can still appear from insects, falling dust, or small movements in the water. If you measure the temperature of a small region of air, it may be slightly warmer or cooler than the average nearby because molecules are always moving and sharing energy unevenly at tiny scales. In a large system at equilibrium, the overall state may be stable, but small local variations can occur. Most are brief, most are small. They appear, fade, and leave no lasting story. But they remind us that equilibrium does not always mean every tiny part is exactly identical at every instant. It means there is no large-scale tendency left to drive organised change. This is an important distinction for the far future. Heat death does not have to mean absolute perfect sameness in every detail. It means the universe has no useful gradients left on ordinary scales. But if the underlying laws include quantum fields, probability, and statistical behaviour, then tiny fluctuations may still be part of the picture. The question is not whether these fluctuations are useful in the way sunlight is useful to a plant or food is useful to a body. They are not. The question is whether the near-empty universe might still have occasional small departures from its quiet background. If it can, then the final state is not a busy future, but it may not be a perfectly blank one either. In everyday thermodynamics, fluctuations are easy to overlook because we live among enormous numbers of particles. A cup of water contains so many molecules that its large-scale behaviour is steady. It cools in the expected direction. It mixes in the expected direction. It does not suddenly gather all its heat into one corner and freeze everywhere else. But if you could observe a tiny enough region for a short enough time, you would find little variations. Some molecules move faster than others. Some regions briefly have slightly more energy. Some have slightly less. These tiny unevennesses are normal. They are part of the microscopic motion hidden beneath the smooth averages we call temperature, pressure, and density. The reason we do not see dramatic reversals is that large fluctuations are fantastically unlikely. A small fluctuation is like a few people in a crowd stepping the other way. A large fluctuation is like the entire crowd suddenly moving backward in perfect coordination, returning every dropped ticket, unspilling every drink, and recreating the exact scene from half an hour earlier. Nothing in the deepest statistical sense says every tiny piece cannot line up in an unusual way, but the chance becomes so small that ordinary language gives up. The universe does not need to forbid such things by command. Probability makes them irrelevant for daily life. In an almost empty eternity, however, the word ordinary becomes tricky. If a system lasts long enough, even events with extremely small chances become tempting to discuss. This is where the far future becomes strange. Imagine a universe that continues for an unlimited time, or for a time so large that it dwarfs every familiar scale. If there are tiny chances for fluctuations, then one may ask what could eventually appear. A small cluster of particles, a slight warm patch, a brief arrangement that resembles something more organised than the background. Most of these would be meaningless and short-lived. They would vanish almost as soon as they appeared. like a faint wrinkle on a dark sea. But the possibility changes how we think about final stillness. It may be quiet beyond all experience, yet not mathematically dead in the simplest sense. Quantum physics deepens the puzzle because empty space is not simply empty in the old common sense. What we call a vacuum is not a perfect nothing. It is the lowest energy state of fields, and fields are the basic physical ingredients that fill space. Even when there are no ordinary particles in a region, the fields still exist, and quantum theory allows them a kind of restless uncertainty. This does not mean that empty space is bubbling like soup in a literal kitchen sense, but it does mean that the vacuum has structure. It can have temporary variations, it can respond to boundaries, it can be influenced by gravity and expansion. So when we imagine the distant future as empty, we should remember that physical emptiness is not the same as no reality at all. There are different ways physicists think about the far future, depending on what dark energy truly is. If dark energy behaves like a constant property of space, the universe may approach a state similar to what is called de Sitter space, named after a physicist who studied such solutions in relativity. In such a future, the expansion continues and distant regions move beyond one another's reach. Space has a horizon, somewhat like the boundary around a black hole, not because there is a solid wall, but because beyond a certain distance signals can never reach an observer. Horizons are connected to temperature and entropy in modern physics, so even this empty expanding future may have a faint thermal character. That idea is subtle, and we do not need the technical details here. The useful point is that the far future may still contain a kind of background thermodynamic behaviour, even when ordinary matter and stars are gone. This leads to a curious possibility. If the universe has a horizon with a faint temperature, then it may not be completely inert. It may allow rare thermal fluctuations. Most would be tiny. The smaller the fluctuation, the more likely it is. The larger and more organised the fluctuation, the more unlikely it becomes. A single particle appearing in some allowed way would be far more plausible than a star appearing. A tiny warm variation would be far more plausible than a planet. A random organised object as complex as a living brain would be so unlikely that the number almost loses meaning. Yet because eternal time gives even absurdly rare events a place in conversation, physicists and philosophers sometimes explore these possibilities to test whether our theories make sense. One famous and rather unsettling idea is sometimes called a Boltzmann brain. The name refers to Ludwig Boltzmann, the physicist whose work helped build the statistical understanding of entropy. The idea is not that actual brains are expected to float around space in any normal future. It is a thought experiment. If a universe in equilibrium lasts forever and allows random fluctuations, then a small self-aware arrangement might be less unlikely than an entire low-entropy universe like ours forming by chance. In that case, one might worry that random observers could outnumber ordinary observers who evolve through stars, planets, chemistry, and biology. This is not a comforting bedtime image, I admit. A lonely brain flickering into existence in the dark is not exactly the sort of thing one wants beside a cup of chamomile tea. But the point is not to frighten anyone. The point is that the idea helps physicists examine whether their cosmological models are reasonable. If a theory predicts too many such absurd observers, that may be a sign that something about the theory needs rethinking. The Boltzmann brain problem also teaches a clearer lesson about fluctuations. The universe we observe is not a tiny fluctuation. It has a deep history. It contains galaxies, cosmic background radiation, stars of different ages, heavy elements, planets, and records that fit together into a coherent past. Our memories are not isolated scraps in a random moment. They are supported by physical evidence around us. Fossils, rocks, starlight, chemical abundances, and the expansion of space all tell a consistent story. The ordinary explanation is that we live in a universe that began in a low entropy state and has been evolving ever since, not that we're a brief random twitch in a dead eternity. fluctuation thought experiments are useful because they remind us how much structure our real universe contains. Tiny fluctuations near heat death would not rebuild that structure in any practical way. To make a new star, matter must gather, heat, compress, and ignite. In the far future, matter may be too spread out, too diluted, or too unavailable. To make a planet, heavy elements must be collected in a stable system. To make life, there must be long-lasting energy flows, chemical complexity, an environment stable enough for evolution. A fluctuation large enough to recreate all of that would be beyond fantastically unlikely. It is better to think of the far future fluctuations as brief local disturbances, not as a reliable path back to cosmic youth. The old universe would not simply wake up refreshed, stretch its arms, and start forming spiral galaxies again. There is another issue. Fluctuations are usually temporary because they are departures from equilibrium. If a small region becomes slightly more ordered or slightly warmer than its surroundings, the same statistical tendency that governs everything else pushes it back toward equilibrium. A tiny concentration spreads out. A small temperature difference fades. A brief arrangement dissolves. In the far future, the background quiet is not easily defeated. It is the default. A fluctuation may appear, but unless it somehow creates a new sustained energy source and a stable environment, it cannot build a long story. It is a spark without fuel. This is very different from the early universe. The early universe had a low entropy condition that was not merely a tiny local accident inside an exhausted background. It was a broad condition from which structure could grow. Gravity could amplify small density differences. Stars could form. Galaxies could develop. The universe had room to create long histories. A random fluctuation near heat death, by contrast, would most likely be local, brief, and isolated. It would not have the same cosmic support. The difference is like comparing a seed planted in a living forest to a speck of dust briefly arranging itself into something seed-shaped in a sealed cold room. Shape alone is not enough. A future requires conditions. Still, the existence of fluctuations means that the far future is not simple absolute silence at every scale. It may be more accurate to imagine a silence with rare, tiny clicks so faint and separated that no listener could gather them into rhythm. The universe may contain isolated events, but no orchestra. It may have statistical twitching, but no sustained activity. It may have possibility in a narrow technical sense, but no practical abundance of possibility. The distinction matters because science often lives in these careful differences. Nothing useful happens is not the same as nothing at all exists. Almost never is not the same as never. Equilibrium is not the same as philosophical emptiness. The idea also highlights how special low entropy really is. We sometimes take order for granted because our daily world is full of it. Houses, trees, bodies, roads, books, clouds, meals, tools, and memories surround us. But all of these depend on a cosmic inheritance. The universe began in a condition that allowed entropy to increase across enormous time. Stars formed because gravity had usable conditions to work with. Planets formed from enriched material. Life formed where energy flowed steadily enough to support complexity. The order we know is not the normal condition of an old exhausted universe. It is temporary flowering in a universe that still has gradients to spend. This does not make the present fragile in a panicked sense. The far future is not arriving tonight, and your tea is in more immediate danger of getting cold than the universe is of losing every star. But it does make the present understandable as part of a thermodynamic middle age. We live before the final dilution, before the last black holes fade, before radiation thins beyond usefulness. The tiny fluctuations of an almost empty eternity show us what remains when the great flows are gone. By contrast, our world is rich with reliable flows. Sunlight arrives every day. Air moves, water cycles, food grows, bodies heal, minds learn. Even sleep is an ordered biological process, a nightly adjustment inside a living system that has not yet run out of energy. There is a gentle irony here. A sleeping person may seem inactive, but sleep is not equilibrium. Sleep is full of regulation, repair, memory processing, temperature changes, hormone cycles, and neural activity. The body is quiet only from the outside. It remains a warm, structured, far from equilibrium system. It can sleep because it is alive, and it is alive because it is constantly exchanging energy with the world. Compared with a heat-death universe, even the stillest bedroom is dazzlingly active. The slow breath under blankets is a thermodynamic achievement. The heart beating in the dark is a small, steady refusal of local equilibrium, made possible by the larger increase of entropy around it. If rare fluctuations occur in the far future, they would not have that support. A random pattern has no ancestry, no metabolism, no environment, no steady source of repair. It appears only because probability, given enough room, can occasionally wander into strange corners. But without a surrounding flow, it cannot persist. This is why the thought of a random ordered object in equilibrium is so different from an organism. Life is not just arrangement, it is arrangement maintained through activity. A brain is not merely a pattern of matter, it is a living organ in a body supplied by blood, oxygen, nutrients, and constant regulation. The context matters. Remove the context, and the pattern cannot remain what it is. Fluctuations also raise questions about recurrence. In some simple systems, if enough time passes, a system might return close to a previous state. This idea is associated with recurrence in statistical mechanics. But applying it to the whole universe is difficult. The universe expands. Gravity complicates the counting of states. Horizons may limit what regions can access. Quantum theory changes what we mean by state. Dark energy may prevent many forms of return. So while recurrence is an interesting mathematical idea, we should be cautious about imagining the entire cosmos simply cycling back to a previous arrangement, like a playlist set to repeat. The far future is not well described by ordinary repetition. Some cosmological models do imagine cycles. A universe expands, contracts, bounces, or gives rise to new regions. These ideas are explored seriously in different forms, but none is confirmed as the answer to our cosmic future. Heat death is not the only idea ever proposed, but it is a major consequence of the current picture of accelerated expansion and increasing entropy. Fluctuations do not automatically turn heat death into rebirth. They simply show that even near equilibrium, physics may still permit rare local deviations. Whether those deviations have any deeper role depends on laws we may not yet fully understand. The almost empty eternity therefore sits between two kinds of thinking. On one side is the strict practical view. No stars, no life, no usable energy, no meaningful activity. On the other side is the subtle statistical view. Tiny fluctuations may still occur, and over vast spans the rare becomes a subject of thought. Both views can be true in their own domains. Practically, the universe is done. Statistically, the universe may still flicker. The flicker does not undo the exhaustion. It only prevents us from calling the future simple nothing. This careful language matters because the end of entropy is not like turning off a light. When a light goes off in a room, darkness comes, but the room remains part of a larger active world. Morning can arrive, someone can flip the switch, electricity can return. In heat death, there is no larger active room in the standard picture. The rare fluctuations belong to the exhausted system itself. They are not rescue. They are the faintest reminders that physical law may still have texture, even when cosmic history has almost no material left to write with. And so the almost empty eternity is not a second beginning, not a hidden paradise of new stars waiting behind the dark, and not a theatrical final curtain. It is a future where the difference between possible and meaningful becomes enormous. A tiny fluctuation may be possible. A lasting world is another matter. A brief local order may appear. A living biosphere requires more than a brief accident. A particle may move. A history requires records. energy and continuity. The universe may still whisper at the edges of probability, but the great conversation of stars and galaxies has faded. From that perspective, the final stillness becomes easier to approach without imagining it as pure absence. It is stillness after nearly all useful contrast has drained away, with only rare fluctuations too small or too isolated to rebuild the bright ages. And it brings us back gently to the meaning of the moment we actually inhabit, a moment full of gradients, warmth, memory, structure, and the simple fact that things are still happening. The almost empty eternity shows us a universe where the difference between possible and meaningful has grown very large. A tiny fluctuation may still be allowed by the rules, but a stable world needs more than a brief accident. A particle may move, but a history needs records. A faint disturbance may appear, but a living system needs an environment that can feed, repair, protect, and continue it. So as we come to the final stillness, we are not imagining a single dramatic moment when the universe suddenly stops, as if someone has leaned over the control panel and switched off the cosmos. We are imagining a long fading of usefulness, a gradual loss of strong differences, a future in which the processes that once made stars, planets, chemistry, weather and life have become too rare or too weak to matter in the familiar way. This final stillness is not simple nothing. It is important to hold on to that distinction. Nothing would mean no space, no fields, no laws, no possibility, no physical state of any kind. Heat death is different. It is a condition where the universe still has whatever remains, but the remaining energy is too spread out, too evenly shared, or too inaccessible to support organized activity. A drained battery is not nothing. A cooled cup of tea is not nothing. A clock with an unwound spring is not nothing. But each has lost the useful difference that allowed it to do what we cared about. The far future of maximum entropy is the cosmic version of that. The parts of reality may remain in some form, but the ability to build new large-scale stories from them has nearly disappeared. This can be difficult to imagine because every experience we have is built from change. Even sitting quietly involves movement. The lungs expand and contract. The heart beats. Heat leaves the body. Nerves carry signals. Cells repair damage. The brain adjusts memories, expectations, and attention. A quiet bedroom is not physically quiet. It is full of air moving, fabric warming, light scattering, circuits operating, and a body maintaining itself far from equilibrium. The stillness we know is always relative. It is calm compared with running, working, speaking, or walking through a crowded street. But compared with the final thermodynamic stillness, even sleep is a tremendous activity. Sleep is not a shutdown. It is a regulated biological state, and regulation means energy flow. The universe near its entropy limit would not have this kind of regulation. There would be no common stars to pour energy into colder surroundings, no planets held in steady warmth, no oceans cycling water through air and cloud, no forests using sunlight, no bodies using food, no brains preserving memories, no machines drawing power from stored chemical or electrical differences. The systems we know depend on being away from equilibrium. They need contrast. They need an uphill and a downhill, a hot and a cold, a before and an after that can leave traces. At the final stillness, those contrasts have almost entirely faded. The universe becomes a place where energy exists, but cannot easily be organized into work. Work in physics does not only mean human labor, it means the ability to make organized change. Lifting a weight, turning a wheel, powering a signal, moving a fluid, building a molecule, repairing a cell, storing a memory, all require usable energy. Usable energy means energy arranged in a way that can flow from one condition to another. A hot object in a cold room can warm the room. Water held above ground can fall and turn a turbine. A battery can push electric charge through a circuit. Food can be broken down by the body. But once the temperature is the same everywhere, Once the water has reached the lowest available level, once the battery is drained, once the food energy has been transformed and released, the system may still contain energy, but it is no longer useful in the same way. The final stillness is the end of useful difference on the larger scale. There is a temptation to treat this as a sad ending to the universe, and in a human sense it does feel empty. We are creatures who care about warmth, memory, continuation, and activity. A future with no stars and no living observers does not offer much comfort, but science is not asking us to feel one specific way about it. It is asking us to understand what the laws imply. The same thermodynamic direction that leads to the final stillness is also the direction that makes the present active. Heat flows from the sun to Earth because the sun is hotter than space. That flow drives weather, photosynthesis, ocean currents, and the long chain of life. If energy did not spread, stars could not warm planets. If entropy did not increase, fuel would not burn, bodies would not metabolize food, memories could not be written in the brain, and causes would not leave effects. The rule that points toward exhaustion is also the rule that allows experience. This is why the final stillness should not be thought of only as loss. It also tells us what the present is. The present is a condition of available differences. The sun is still bright. Space is still cold. Earth still receives energy and sends energy away. The atmosphere still moves. The oceans still carry heat. Living things still maintain themselves. Your body, right now, is a small structure holding itself together by constant exchange with the world. It takes in oxygen, uses stored chemical energy, releases heat, moves fluids, repairs tissues, and keeps a careful internal balance. It is not separate from entropy. It is a temporary ordered process made possible by entropy increasing elsewhere. That may sound less romantic than saying life is magic, but it is not less astonishing. It means every living moment is a maintained pattern in a universe that allows patterns to appear for a time. The far future also makes clear that permanence is not the only measure of importance. Stars are not permanent, but they matter. A candle is not permanent, but it lights a room while it burns. A conversation is not permanent, but it can change the state of a mind. A meal is not permanent, but it becomes movement, warmth, repair, and memory. A human life is not permanent, but it is not therefore meaningless. Physics often strips away illusions of permanence, but it does not strip away reality. Temporary things are still real. Processes are still real. A song exists while it is played, not because it lasts forever, but because it has structure, duration, and effect. A living body exists as a process, not as a fixed object. A civilization exists as activity maintained across generations. The universe itself, in its bright eras, is not a static possession. It is an unfolding physical process. When we think about entropy reaching its limit, we also learn that order is not free. Every ordered system requires conditions. A clean room requires effort. A living cell requires metabolism. A city requires energy supply, repair, transport, food, water, and information. A scientific instrument requires power, calibration, protection, and maintenance. Even a memory requires a brain capable of preserving it. The final stillness is what remains when the conditions for maintenance are gone. That does not make maintenance pointless. It makes maintenance central. Everything we value in the physical world is not merely made once. It is kept going. A body must keep itself alive. A relationship must be renewed through attention. A home must be cared for. Knowledge must be stored, taught, checked, and corrected. Order persists where energy and care are available. At the cosmic scale, no act of care can stop entropy from increasing overall. That is not a failure of care. It is simply the scale of the law. But locally, for a while, energy can be directed. A room can be warmed. A garden can be planted. A child can be fed. A wound can heal. A telescope can gather faint light from another galaxy. A mind can learn how stars die and why black holes may not last forever. These local acts do not overturn thermodynamics. They are examples of thermodynamics working through living systems. The universe permits pockets of order because energy flows through them. The fact that they are temporary does not make them illusions. It makes them events. The final stillness also changes how we understand time. In ordinary life, time is packed with markers: meals, alarms, seasons, birthdays, departures, arrivals, sunrise, sunset. In physics, time can be measured by change, and change requires distinguishable states. Near heat death, there may still be time in a theoretical sense depending on the deeper nature of the universe, but there would be few processes left to mark it. Without stars, there are no days for planets in the ordinary living sense. Without stable observers, there are no memories. Without usable energy, clocks cannot be built or maintained. The universe may continue, but continuation without records is hard to call history. Time becomes difficult to notice when nothing organized remains to notice it. That thought brings us back to the importance of records. Everything we know about the past comes from traces in the present. Fossils, rocks, light from distant galaxies, chemical patterns, written words, photographs, memories and scars are all records. They exist because physical processes left marks. Entropy is involved in making those marks possible. A footprint forms because sand is rearranged. A photograph forms because light changes a sensor or surface. A memory forms because the brain changes. The final stillness is a future with no new meaningful records, and with old records long dispersed or destroyed. The story of the universe may still be encoded in some deep physical state, but not in a way that any observer could read. A book burned to ash has not made its atoms vanish, but the book as a readable object is gone. This is why the present is not only a moment, but a rare kind of physical situation. It contains readable records and active processes at the same time. We can see old starlight and make new measurements. We can study ancient rocks and write new explanations. We can inherit memories and create fresh ones. The universe has not yet become too smooth, too cold, or too dilute to support inquiry. Science itself is a thermodynamic activity. It requires brains, instruments, energy, stable environments, communication, and memory. A universe at maximum entropy would not wonder about maximum entropy. The question can only be asked during a time when the universe is still far from that limit. There is comfort in recognizing this, but it is not the comfort of pretending the far future is different from what physics suggests. It is the comfort of placing ourselves accurately in the story. We are not living at the final stillness. We are living in a bright and active interval. The stars are still there. The sun still rises for Earth. Food still grows. Water still cycles. Matter still forms bodies capable of awareness. The conditions that allow a person to lie quietly and listen to a discussion of entropy are not ordinary in the full sweep of cosmic time. They are specific, temporary, and remarkable. The universe does not have to last forever in its current form for this moment to be real. This does not mean every moment must be treated with urgency. In fact, the subject may invite the opposite. Cosmic timescales are so vast that our usual hurry seems smaller. Entropy is not chasing us around the room with a clipboard. The stars will not vanish because a cup was left unwashed. The far future is not a reason to panic. It is a reason to understand. The universe changes through lawful processes, and we live within those processes for a while. That can make ordinary rest feel more acceptable. A living system cannot only act, it must also recover. Sleep, stillness, and quiet are not failures to use time. They are part of the maintenance of order in a body that needs care. Even rest belongs to thermodynamics. The final stillness also helps separate useful fear from unnecessary fear. It is reasonable to care about the future of life, the planet, and the energy systems we use, because those are near enough for choices to matter. The heat death of the universe is not near in any practical human sense. It is not a disaster to prepare for on a calendar. It is a boundary in our understanding of physical possibility. It gives perspective, not a task list. It tells us that energy matters, gradients matter, maintenance matters, and temporary order is precious because it depends on real conditions. But it does not ask us to solve the final fate of the cosmos before breakfast. If anything, the long view can make the local view clearer. A warm room matters because warmth is a physical condition that can be lost. A kind word matters because it changes the state of a person who can remember it. A scientific idea matters because it can be held, tested, revised, and passed on while records still exist. A quiet night matters because the body uses it to recover. The meaning of this moment is not found by pretending it will last forever. It is found by seeing that it is part of a temporary active universe, and that temporary things can still have consequences. The final stillness is almost impossible to picture fully, because every picture we make contains objects, boundaries, contrast, and sequence. We imagine darkness, but darkness itself is a contrast with light. We imagine emptiness, but emptiness is imagined from a mind used to rooms and skies. We imagine time passing, but passing requires change. The actual far future may be stranger and less imaginable than any simple scene. It may not look like anything, because looking requires light, eyes, brains, and time marked by perception. In a universe with no observers, appearance is not the right category. The universe does not need to look dark to anyone in order to be dark. Yet our inability to picture it perfectly is not a failure. It is a sign that our minds evolved in a rich environment, not in heat death. We are built to track motion, sound, food, danger, weather, faces, tools, and stories. We are not built to intuit horizons in an accelerating universe, black hole evaporation, or entropy across spans longer than the life of every star. Science lets us extend thought beyond intuition, but it does not require us to feel at home there. It is enough to understand the direction in broad terms. Energy spreads, differences fade, useful work becomes harder, stars burn out, black holes remain and then may fade. Fluctuations may whisper in the long quiet. The final stillness is the limit approached when the universe has almost nothing left from which to build activity. And after all of that, here we are, not in that stillness, but in a room, or a bed, or a chair, or wherever you happen to be listening. There is probably some small sound nearby. A wall settling, a car passing, a breath, a device humming faintly. There may be a light on, or perhaps only the glow of a screen. All of it is part of the active universe. Energy is being used, signals are being carried, matter is arranged in a way that allows thought. The final stillness is distant, but the laws that point toward it are here with you in every ordinary process. The cooling air, the slowing heartbeat before sleep, the warmth under a blanket, the tired brain releasing the day one thought at a time. So perhaps the meaning of this moment is not that it defeats entropy. It does not. Nothing we do cancels the larger thermodynamic direction. The meaning is that, for now, entropy has not reached its limit. The universe still has room for structure, repair, curiosity, memory, and rest. It still has enough contrast for stars to shine and minds to ask what shining means. It still has enough order for a voice to become sound, sound to become thought, and thought to become a calm awareness of being here. That is not a small thing. It is a physical event in a universe that will not always make such events easy. And if this long journey through entropy, stars, black holes, heat death, and the far future has helped your thoughts slow down, I am grateful you spent this time here. If it brought you a little calm or gave you something quiet to think about as the night settles, a like and a subscription help this gentle corner of science reach others who may need the same kind of rest. But for now, there is nothing urgent left to hold. The universe is still active. The stars are still shining. Your body is still keeping its careful rhythm. Let the final stillness remain where it belongs, far beyond the reach of tonight, while this moment does its simple work. Sleep well wherever you are and let the warmth you have be enough for now.